Mars has survived asteroid impacts, global dust storms, and 4 billion years of cosmic bombardment, but it has never faced anything like 3I-ATLAS. This interstellar wanderer carries ice and chemistry forged under an alien sun, and its approach to Mars represents humanity's first test of how well we understand cosmic threats from beyond our solar neighborhood. The October 3rd encounter could unfold as a routine gravitational dance, or it could trigger cascading catastrophes that transform Mars from our next home into our greatest warning. From impact scenarios that create 30-kilometer craters to contamination that introduces alien chemistry to an entire planet, the range of possible outcomes defies comfortable prediction. Tonight, we'll examine why the worst-case scenario might not involve Atlas hitting Mars at all, but something far more subtle and potentially permanent. Stay until the end to understand why the scariest outcome might not be impact at all, but something far more insidious. Part 1. October 3rd. The Moment of Truth. October 3rd, 2025. Mark this date in your calendar, because it won't happen again. On this seemingly ordinary Friday, something extraordinary will unfold in the void between worlds. A cosmic dance that could rewrite the rules of planetary safety as we know them. 3I-ATLAS, our mysterious visitor from beyond the stars, will sweep past Mars at a distance of roughly 30 million kilometers. In terrestrial terms, that sounds comfortably distant, about 75 times the distance from Earth to our moon. But in the realm of interstellar wanderers, this represents what astronomers call an uncomfortably close shave. The European Space Agency has been tracking this encounter with the kind of nervous precision usually reserved for defusing bombs. Their calculations paint a picture of celestial mechanics gone slightly mad. Atlas isn't behaving like the well-mannered comets we're accustomed to in our solar neighborhood. This thing has been throwing cosmic tantrums since we first spotted it, and October 3rd might be when it finally loses its interstellar composure completely. Consider the evidence that's been accumulating like storm clouds on a summer horizon. Atlas has been generating a carbon dioxide coma of staggering proportions, a billowing shroud of gas that extends millions of kilometers in every direction. Most comets save their dramatic displays for when they're much closer to the Sunday Atlas, however, seems to have missed that particular memo from the Cosmic Etiquette Handbook. The brightness surges have been equally troubling. Multiple observatories have reported flare-ups that arrive without warning and fade just as suddenly. These aren't the gentle, predictable changes we expect from a chunk of ice slowly warming in sunlight. These are the erratic outbursts of something fundamentally unstable, something that might be holding itself together through sheer cosmic willpower. NASA's SPHEREX telescope has been working overtime to catalogue these anomalies, and the data creates a picture that would make any planetary defense specialist reach for the antacids. The plume geometry looks wrong. The gas emissions follow patterns that don't match our models. Even the orbit itself carries subtle perturbations that suggest this isn't just a simple dirty snowball from the outer reaches of another star system. But here's where things get genuinely concerning. As Atlas approaches its closest point to Mars, we're entering what astronomers politely call a visibility gap. Solar conjunction, the moment when Mars, the Sun, and Earth align in a way that makes clear observation nearly impossible, is approaching. For several weeks, our ability to monitor this cosmic interloper will be severely compromised. Think about that for a moment. Just when Atlas reaches its most critical phase, just when its proximity to Mars could trigger the most dramatic events, we're essentially flying blind. It's like trying to watch a high-stakes poker game through a keyhole while wearing a blindfold. This timing couldn't be more suspicious if it had been planned by some malevolent cosmic intelligence. The universe, it seems, has a twisted sense of humor when it comes to keeping us guessing about the fate of our neighboring planet. The scientific community is walking a delicate line between professional skepticism and barely contained panic. Rapid activity changes in comets often serve as harbingers of fragmentation events. When a comet starts behaving erratically, when its coma brightens unexpectedly, when its emissions follow chaotic patterns, experienced astronomers start preparing for the possibility that the object might simply fall apart. Now imagine that fragmentation event occurring not in the safe depths of interstellar space but within spitting distance of Mars. Picture kilometre-scale chunks of ancient ice and rock suddenly liberated from their parent body, each following its own trajectory through the gravitational maze of the inner solar system. Some might spiral sunward, adding to the growing population of potentially hazardous objects. Others might find themselves on collision courses with planets that have spent billions of years in peaceful isolation. The European Space Agency's models suggest that even without a direct impact, the gravitational perturbations from a major fragmentation event could nudge some debris into orbital paths that intersect with Mars's trajectory for years or even decades to come. We might be witnessing not just a single close encounter, but the seeding of a cosmic minefield that will plague Mars exploration efforts for generations. What makes this scenario particularly unsettling is our ignorance about Atlas's true nature. The massive coma obscures our view of the actual nucleus. We don't know if we're dealing with a single massive object, a loose collection of fragments already barely held together by gravity, or something even more exotic. The glowing shroud that makes Atlas so visually spectacular might be hiding a cosmic time bomb whose detonation could scatter debris across multiple planetary orbits. NASA's Science Mission Directorate has been conspicuously quiet about specific contingency plans, though sources within the agency suggest that multiple Mars orbiters are being positioned to capture whatever data they can during the encounter. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Trace Gas Orbiter represent humanity's eyes and ears at Mars. If something dramatic occurs on October 3rd, these robotic sentinels will be our only witnesses to events that could reshape our understanding of interstellar visitors. But even these sophisticated instruments operate under significant constraints. Their cameras and spectrometers were designed to study Mars, not to track high-velocity cosmic debris. Their communication systems were built for routine data transmission, not for emergency broadcasts about planetary catastrophes. If Atlas decides to put on a truly spectacular show, our Mars-based assets might find themselves woefully unprepared for the cosmic fireworks. The promise of this investigation extends far beyond mere scientific curiosity. We're going to follow the evidence wherever it leads, even if it takes us into territories that make comfortable assumptions about planetary safety seem dangerously naive. We'll examine the collision scenarios that keep planetary defense specialists awake at night. We'll explore atmospheric effects that could turn Mars into a toxic wasteland. We'll consider contamination possibilities that could complicate humanity's plans for Mars colonization for centuries to come. Most importantly, we'll ask the questions that official agencies seem reluctant to pose in public. What if Atlas isn't just passing by? What if October 3rd marks the beginning of something far more sinister than a simple gravitational encounter? The answers might surprise you. They might terrify you. But one thing is certain. After October 3rd, nothing about our relationship with interstellar visitors will ever be quite the same. The collision scenario we're about to explore represents just the tip of a cosmic iceberg that extends far deeper into the realm of planetary catastrophe than most people dare to imagine. Part 2. The collision scenario. The mathematics of cosmic destruction are surprisingly elegant. When astronomers calculate the probability of Atlas actually striking Mars on October 3rd, the numbers initially seem reassuring. At a distance of 0.19 to 0.2 astronomical units, the geometry suggests that a direct collision falls somewhere between astronomically unlikely and physically impossible. But mathematics, like democracy, works best when everyone follows the rules. And Atlas, as we've established, appears to be something of a cosmic anarchist. Consider what would happen if one of those mysterious fragmentation events we discussed earlier occurred at precisely the wrong moment. Picture Atlas holding itself together through 30,000 years of interstellar travel, only to come apart like a poorly constructed firework just as it reaches Mars's gravitational neighborhood. The parent body might continue on its predictable trajectory, passing harmlessly by the red planet, but the fragments would write their own rules. Each piece of debris would carry its own momentum, modified by the chaotic forces of the breakup event. Some might accelerate toward the Sunday, others might be deflected outward, beginning their own lonely journeys toward the stars. But a few, perhaps just a handful out of hundreds of fragments, might find their trajectories bent just enough by Mars's gravitational influence to transform a near miss into a direct hit. Let's scale the destruction to understand what we're really facing. A fragment measuring 100 to 500 meters across, roughly the size of a city block, would arrive at Mars traveling at velocities that make rifle bullets look sluggish. The kinetic energy involved would equal thousands of nuclear weapons detonating simultaneously. The resulting crater would span several kilometers, but that's just the beginning of Mars's troubles. Mars's atmosphere, thin and composed primarily of carbon dioxide, offers virtually no protection against incoming projectiles. Unlike Earth's thick atmospheric blanket, which can burn up smaller objects and slow larger ones, Mars might as well be naked to cosmic assault. The impact energy that would be partially absorbed by Earth's atmosphere would instead be delivered directly to the Martian surface with undiminished fury. The immediate aftermath would transform Mars into a world barely recognizable to the robotic explorers that have been studying it for decades. Impact ejecta, pulverized rock, and ancient permafrost would be hurled high into the tenuous atmosphere, creating a planet-wide dust storm that would make the seasonal storms we've observed look like gentle breezes. The opacity of the Martian sky would spike beyond anything in the historical record. Within hours, the entire planet would be shrouded in a choking veil of suspended particles. Solar panels on rovers and landers would become useless, starved of the sunlight they need to function. Temperatures would plummet as dust blocked incoming solar radiation, triggering a nuclear winter effect that could persist for months or even years. But the electromagnetic chaos might pose an even greater threat to our technological assets than the dust itself. The impact would generate intense electromagnetic pulses as charged particles from the expanding fireball interact with Mars's weak magnetic field. These pulses could induce damaging currents in electronic systems, potentially crippling spacecraft that survived the initial blast. The Mars Reconnaissance Orbiter, MAVEN, the Trace Gas Orbiter, and Mars Express, our electronic ambassadors circling the red planet, would suddenly find themselves operating in an environment more hostile than anything their designers anticipated. Star trackers might lose their ability to navigate. Communication systems might be overwhelmed by radio interference from the ionized debris cloud. Solar arrays might suffer damage from high-velocity particles accelerated by the impact. On the surface, the consequences would be even more severe. The Perseverance and Curiosity rovers, along with the InSight lander, have been designed to weather normal Martian dust storms. But a planet-wide dust hurricane triggered by a cosmic impact represents a completely different category of challenge. Communication with Earth would become sporadic at best, as atmospheric conditions interfere with radio transmissions. The radiation environment around Mars would spike dramatically as the impact excavates subsurface materials and lofts them high into the pound. Atmosphere. The thin atmospheric layer that provides Mars with minimal radiation shielding would become saturated with charged particles, creating hazardous conditions for any future human explorers. Even robotic systems would face increased risk of radiation-induced failures. Now let's escalate the scenario to truly apocalyptic proportions. What if instead of a single fragment, multiple pieces of Atlas found their way to Mars? What if the fragmentation event produced not just one city block-sized projectile, but dozens? The cumulative effects would push Mars beyond a mere bad day into the realm of planetary catastrophe. Multiple impacts would create overlapping ejecta clouds, turning the entire planet into a chaotic storm of debris. The combined electromagnetic effects would create radio blackouts lasting for months. The dust opacity would reach levels that completely block solar radiation, triggering a planetary ice age that could alter Mars's climate for centuries. But here's where the scenario becomes truly unsettling for those of us still safely orbiting Earth. The gravitational chaos created by multiple impacts could alter the orbits of Mars's two small moons, Phobos and Deimos. These irregular chunks of rock are already unstable. Phobos is gradually spiraling inward and will eventually crash into Mars anyway, though not for another 50 million years or so. A major disruption could accelerate this timeline dramatically. If impact ejecta were to strike Phobos with sufficient force, or if gravitational perturbations from Atlas fragments were to destabilize its orbit, we could witness the destruction of a moon in real time. The debris from such an event would create a ring system around Mars, but not the elegant, stable rings of Saturn. Instead, we'd be looking at a chaotic cloud of rocky fragments that would pose a navigation hazard for centuries to come. The psychological impact on Earth would be profound. Mars represents humanity's next frontier, our backup, plan, our second chance at becoming a spacefaring civilization. To watch it transformed into a radiation-soaked wasteland, orbited by the debris of its own destroyed moon, would be like watching our future crumble in real time. Yet even this catastrophic scenario pales in comparison to the possibility that we've been thinking too small. What if the real danger isn't mechanical destruction, but something far more subtle and potentially permanent? What if the October 3rd encounter delivers not just rocks and ice, but something that could poison Mars's potential for human habitation in ways we're only beginning to understand? The atmospheric shockwave scenario we're about to explore doesn't require a single fragment to actually strike the planet. Part 3. The atmospheric shockwave. Forget everything you think you know about cosmic impacts. The most insidious threats from ATLAS might never actually touch Mars at all. Mars's defenses against cosmic assault are, to put it charitably, pathetic. Unlike Earth, which wraps itself in a protective magnetic cocoon that deflects most charged particles, Mars stands naked before the solar wind. Its global magnetic field died billions of years ago, leaving behind only scattered magnetic anomalies, cosmic scars that serve as tombstones for the planet's former protective shield. This magnetic nakedness makes Mars exquisitely vulnerable to effects that Earth's magnetosphere would shrug off without breaking a sweat. When ATLAS sweeps past Mars trailing its enormous carbon dioxide coma and potentially shedding debris, it won't be delivering a conventional shockwave in the Hollywood sense. There won't be a wall of compressed air racing across the Martian landscape at supersonic speeds. Instead, we're looking at something far more subtle and potentially more devastating, an electromagnetic and particle cascade that could fundamentally alter Mars's atmospheric chemistry and electrical environment for months or even years. Picture ATLAS as it approaches Mars, its nucleus venting gases and particles in chaotic bursts that we've been documenting throughout 2025. Each outburst creates expanding clouds of ionized material, essentially plasma, that interact with the solar wind in complex ways. As this ionized cocktail encounters Mars's weak magnetic field remnants, it doesn't simply bounce off, it penetrates, it swirls. It creates electromagnetic eddies that can persist long after ATLAS itself has continued on its trajectory. The immediate effect would be a dramatic enhancement of Mars's already meager auroral displays. Instead of the faint, localized glows that Mars occasionally produces, we might witness planet-wide light shows as charged particles from ATLAS's coma cascade into the upper atmosphere. These auroras wouldn't be the gentle, romantic displays that northern Earth enjoys. They'd be angry, chaotic storms of light that would interfere with radio communications and potentially damage sensitive electronic equipment. But the visible effects represent only the tip of the electromagnetic iceberg. The real chaos would occur in Mars's ionosphere, the electrically charged layer of the upper atmosphere that our orbiting spacecraft rely on for communications. As ATLAS's charged particles interact with this region, they would create radio blackout windows that could last for weeks. Think about the implications for our robotic explorers. The Mars rovers have grown accustomed to reliable communication windows with Earth, carefully scheduled sessions where they upload their discoveries and download new instructions. An ionospheric disruption could sever these digital lifelines, leaving billion-dollar robots effectively stranded on an alien world, unable to report their status or receive guidance from their human controllers. The electromagnetic chaos wouldn't stop at the ionosphere. Mars's thin atmosphere makes it particularly susceptible to electrostatic effects that would barely register on a world with a robust atmospheric envelope. As ATLAS's debris field interacts with the Martian environment, it could create conditions similar to the massive dust devils that already plague the planet, but supercharged with electrical potential. Imagine dust storms where individual particles carry significant electrical charges, creating lightning displays that dwarf anything Earth has ever witnessed. These wouldn't be the relatively gentle static discharges we observe in terrestrial thunderstorms. They'd be violent arcs of electrical energy capable of damaging surface equipment and creating radio frequency interference that would make communication with Earth virtually impossible. The scenario becomes genuinely alarming when we consider Mars's propensity for global dust storms. These planet-wide tempests can begin from seemingly minor triggers, a small temperature differential here, a pressure change there. The electromagnetic chaos from Atlas's passage could provide exactly the kind of trigger needed to nudge Mars's atmospheric system over the edge into one of these global catastrophes. But here's where atmospheric physics gets truly disturbing. What if Atlas's passage doesn't just trigger a conventional dust storm, but creates something entirely new in the annals of planetary meteorology? What if the combination of charged particles from the comet's coma and Mars's existing atmospheric dynamics creates a feedback loop that becomes self-sustaining? Picture this nightmare scenario. Atlas's charged debris creates initial electromagnetic disturbances in Mars's upper atmosphere. These disturbances generate static electricity in the lower atmosphere, which charges dust particles and makes them more likely to become airborne. The increased dust loading alters the planet's energy balance, creating temperature and pressure differentials that sustain the storm. Meanwhile, the charged dust particles continue to interact with what remains of Mars's magnetic field, perpetuating the electromagnetic chaos. The result would be a planet trapped in a quasi-permanent state of electromagnetic and meteorological turmoil, a feedback loop from hell that could persist for years after Atlas has continued on its journey toward the outer solar system. Mars would become a world where dust storms never end, where radio communications are sporadic at best, and where the radiation environment is so chaotic that even our hardiest robotic explorers might succumb to electronic failures. NASA's spacecraft designers have anticipated many challenges for Mars operations, but they've never had to contend with a planet-wide electromagnetic tornado. The Mars Reconnaissance Orbiter's high-gain antenna might find itself constantly fighting interference from charged dust clouds. MAVEN's particle detectors, designed to study the gentle solar wind interactions with Mars's upper atmosphere, might be overwhelmed by the chaotic particle environment created by Atlas's passage. The public relations nightmare would be immediate and profound. As images from Mars become sporadic and communication windows disappear, speculation would run wild. Social media would explode with theories about what's really happening to our robotic emissaries on the Red Planet. Official denials and technical explanations would be drowned out by more sensational narratives about cosmic catastrophes and government cover-ups. But perhaps the most unsettling aspect of this scenario is how it would be misunderstood by the general public. Mars wouldn't actually be on fire in any conventional sense. Carbon dioxide doesn't support combustion the way oxygen does. But the global auroral displays, the constant lightning from charged dust storms, and the eerie electromagnetic phenomena would create visual effects that could easily be misinterpreted as planetary conflagration. The scientific community would find itself in the awkward position of trying to explain that Mars hasn't actually ignited, while simultaneously acknowledging that the planet has indeed become temporarily uninhabitable for human exploration. The distinction between chemically burning and electromagnetically chaotic would be lost on a public already primed by decades of disaster movies to expect the worst possible interpretations of cosmic events. Yet even as we contemplate these electromagnetic nightmares, we must acknowledge that Mars's atmospheric chaos might not be the worst-case scenario. What if Atlas brings something to Mars that's far more persistent than electromagnetic storms, far more dangerous than charged dust clouds? What if the real threat isn't physical or chemical, but biological? A contamination from another star that could fundamentally alter not just Mars's immediate future, but humanity's long-term relationship with the Red Planet? The contamination scenario we're about to explore operates on timescales that make electromagnetic storms look like brief summer squalls. Part 4. Contamination from another star. The concept of panspermia, life hitchhiking between worlds on cosmic debris, has tantalized scientists for decades. But when that cosmic debris originates from another star system entirely, the implications become profound enough to keep astrobiologists awake at night. Atlas presents us with a disturbing possibility that no one in the scientific establishment seems eager to discuss in public. This interstellar wanderer has spent at least 30,000 years travelling through the void between stars, its nucleus acting as a cosmic deep freeze, preserving whatever molecular cargo it might have picked up during its formation in an alien stellar system. The massive carbon dioxide coma that Atlas has been generating provides the perfect chemical environment for complex organic molecules to survive and even evolve during interstellar transit. Carbon dioxide isn't just a simple waste gas, it's an excellent solvent for organic chemistry, capable of stabilizing complex molecular structures across the temperature and pressure ranges that Atlas has experienced during its journey. NASA's James Webb Space Telescope has been conducting spectroscopic analysis of Atlas's coma, though the results remain frustratingly preliminary. The infrared signatures detected so far confirm the presence of carbon dioxide, water vapor, and what mission scientists diplomatically describe as complex organic species. But the true nature of these organic components remains hidden behind layers of technical analysis and peer review that could take months to complete. Meanwhile, the SphereX mission has been tracking subtle changes in Atlas's emissions that suggest something more dynamic than simple sublimation of frozen gases. The patterns detected don't match the behavior of conventional comets warming in sunlight. Instead, they hint at chemical processes that might be ongoing within the coma itself, possibly catalyzed by cosmic radiation or internal chemical reactions that have been proceeding slowly but steadily during the object's interstellar voyage. Planetary protection protocols exist specifically to prevent cross-contamination between worlds, but these procedures were designed for spacecraft traveling between planets within our solar system. No one has seriously considered what happens when an entire alien ecosystem potentially arrives at Mars without any sterilization procedures whatsoever. The October 3rd encounter could deliver organic molecules to Mars that have never existed on any planet in our solar system. These compounds, evolved under the chemical conditions of an alien stellar environment, might interact with Martian soil and atmosphere in ways that our models can't predict. They might catalyze reactions that alter the planet's chemical balance. They might introduce molecular templates that could interfere with future searches for indigenous Martian life. Consider the nightmare scenario that keeps planetary protection specialists reaching for their emergency contact lists. Exotic organic molecules from Atlas integrate with Mars's regolith and begin self-organizing into structures that mimic biological processes. These wouldn't necessarily be alive in any sense we would recognize, but they might be active enough to alter local chemistry, consume resources, and spread through environmental mechanisms. Such pseudo-biological activity could render Mars unsuitable for human habitation long before we develop the technology to establish permanent colonies there. Imagine trying to set up life support systems on a planet where the soil itself has been contaminated with self-replicating chemistry that we don't understand and can't control. The risk assessment for human missions would have to be completely rewritten. Even more troubling is the possibility of false positives in future life detection experiments. Mars exploration has always been driven by the tantalizing possibility that we might discover evidence of past or present life on the red planet. Sophisticated instruments currently being developed for future Mars sample return missions are designed to detect the subtle chemical signatures that might indicate biological processes. But what happens when those same instruments encounter organic molecules that originated from Atlas? How do we distinguish between indigenous Martian biochemistry and contamination from an interstellar visitor? The scientific implications could set back our understanding of Mars by decades, as researchers struggle to separate local signals from cosmic noise. The contamination scenario becomes even more complex when we consider the potential for atmospheric distribution. If Atlas's approach triggers the kind of global dust storms we discussed earlier, any organic molecules deposited on the Martian surface could become airborne and spread across the entire planet within weeks. What might begin as localized contamination could become a planet-wide phenomenon that affects every future landing site. NASA's current Mars exploration timeline includes ambitious plans for human missions in the 2030s. These missions depend on the assumption that Mars represents a relatively predictable environment where life support systems can function reliably and where in-situ resource utilization can provide the water, oxygen, and even fuel needed for sustained human presence. Organic contamination from Atlas could undermine these assumptions completely. Water extraction systems might become clogged with alien organic compounds. Atmospheric processes might be overwhelmed by chemical reactions they weren't designed to handle. Even the psychological impact on human crews could be devastating. Imagine being the first humans to set foot on Mars, only to discover that the planet has been fundamentally altered by contamination from an interstellar visitor. The timeline for understanding these effects could span decades. Unlike impact craters or electromagnetic storms, which reveal their consequences relatively quickly, chemical and biological contamination operates on much longer timescales. We might not fully understand what Atlas has done to Mars until well into the 2060s or beyond. The scientific community faces a particularly uncomfortable dilemma in discussing these possibilities publicly. Acknowledging the contamination risk might be interpreted as fear-mongering, potentially undermining public support for Mars exploration programs that have taken decades to develop and billions of dollars to implement. But failing to acknowledge these risks could leave future missions unprepared for environmental conditions that differ dramatically from current models. International space law provides little guidance for scenarios involving contamination from interstellar objects. The Outer Space Treaty and subsequent agreements were crafted with human-caused contamination in mind, not cosmic delivery of alien chemistry. If Atlas does contaminate Mars, there's no clear legal framework for determining responsibility or coordinating the international response. The contamination scenario also raises profound questions about planetary ethics. Do we have the right to continue exploring Mars if that exploration might be compromised by contamination we can't control? Should future missions be postponed until we better understand what Atlas might have delivered to the Red Planet? These aren't just technical questions, they're moral ones that could reshape humanity's approach to space exploration for generations to come. Yet even as we grapple with these biological nightmares, we must remember that Atlas operates in a realm where physics itself can become chaotic. The gravitational dance between planets, moons, and cosmic debris follows rules that can produce outcomes far more dramatic than simple contamination. What if the October 3rd encounter doesn't just alter Mars's chemistry but fundamentally disrupts the gravitational relationships that have kept the Martian system stable for billions of years? The orbital chaos scenario we're about to explore operates on scales that make biological contamination look almost quaint by comparison. Part 5. Orbital Chaos. Phobos and Deimos, Mars's two diminutive moons, have been described by astronomers as captured asteroids, irregular chunks of rock that Mars managed to gravitationally snare at some point in its distant past. But these cosmic prisoners are hardly model inmates. Phobos, the larger and inner of the two moons, is already serving a death sentence, spiraling slowly inward toward an inevitable collision with Mars in approximately 50 million years. Under normal circumstances, this timeline provides plenty of breathing room for human civilization to establish itself on Mars and figure out what to do about the eventual moon crash scenario. But Atlas's approach on October 3rd introduces variables that could dramatically accelerate this cosmic execution schedule. The gravitational reality of Atlas's encounter presents us with an interesting paradox. At a distance of 30 million kilometers, the comet's direct gravitational influence on Phobos and Deimos would be negligible, roughly equivalent to the gravitational pull of a large building on Earth trying to influence the Moon's orbit. The mathematics simply don't support scenarios where Atlas reaches out with invisible hands to grab Mars's moons and fling them into new trajectories. But chaos theory teaches us that small influences can have large consequences when systems are already near critical transitions. And Phobos, as it turns out, exists in a state of gravitational precariousness that makes it exquisitely sensitive to even minor perturbations. The Moon orbits Mars at an altitude of only about 6,000 kilometers, so close that it completes 3 orbits per Martian day. This proximity places Phobos well within Mars's Roche limit, the distance at which tidal forces from the planet overcome the Moon's own gravity. The only thing keeping Phobos from disintegrating immediately is the internal strength of its rocky structure, and even that is gradually giving way to the relentless tidal stresses. Recent observations have revealed that Phobos is already showing stress fractures, parallel grooves that may represent the early stages of tidal breakup. The Moon is literally being pulled apart by Mars's gravity, grain by grain, orbit by orbit. It's a cosmic death by 1,000 cuts that has been proceeding for millions of years. Now, Introduce ATLAS into this delicate gravitational ballet. The comet might not exert enough direct gravitational influence to matter, but it brings something potentially more dangerous: debris. As ATLAS sweeps through Mars's gravitational neighborhood, it could shed material that intersects with the orbital planes of the Martian moons. Even tiny particles, when they're traveling at interstellar velocities, carry tremendous kinetic energy. A grain of sand from Atlas's coma, striking Phobos at 20 kilometers per second, would impact with the force of a small explosive device. Multiply this by thousands or even millions of particles, and you begin to understand how a seemingly gentle cosmic encounter could become a devastating bombardment. The cumulative effect of such impacts might be enough to push Phobos's already stressed structure beyond its breaking point. Instead of gradually disintegrating over millions of years, the Moon could fragment catastrophically during or shortly after Atlas's passage. What has been a slow-motion cosmic demolition project could become a sudden explosion of debris. But let's escalate this scenario to its logical extreme. What if Atlas doesn't just accelerate Phobos's demise, but creates something entirely new in the annals of planetary science? What if the encounter generates enough debris to create Mars's first ring system? The physics of planetary rings are more complex than most people realize. Saturn's elegant ring system represents a delicate balance between gravitational forces, particle collisions, and electromagnetic effects that took millions of years to achieve stability. A ring system, created by the violent fragmentation of Phobos, would be nothing like Saturn's orderly bands of ice and rock. Instead, Mars would find itself surrounded by a chaotic cloud of debris following wildly elliptical orbits. Some fragments would be large enough to pose serious hazards to spacecraft operations. Others would be small enough to create a persistent micrometeoroid environment that could sandblast solar panels and optical instruments over time. The navigation challenges for future Mars missions would become nightmarish. Instead of planning trajectories around two small, predictable moons, mission planners would have to contend with thousands of fragments following unpredictable paths. The risk of collision would increase exponentially, potentially making Mars orbit too dangerous for routine spacecraft operations. But orbital mechanics has a cruel sense of humor when it comes to cleanup operations. Unlike terrestrial pollution, which can sometimes be remediated through human intervention, orbital debris follows the immutable laws of physics. Every collision between fragments creates more fragments, each following its own trajectory. The process feeds on itself, creating cascade effects that can persist for centuries. This is known in space operations circles as the Kessler syndrome, a runaway chain reaction of orbital collisions that renders entire regions of space unusable for practical operations. We've been worried about this phenomenon affecting Earth's orbital environment for decades. But Mars, with its weaker gravitational field and thinner atmosphere, might be even more vulnerable to such cascading destruction. The psychological impact on humanity's Mars colonization dreams would be profound. For decades, we've envisioned Mars as our backup planet, our second chance at building a sustainable civilization beyond Earth. To watch that future literally fragment before our eyes would be like witnessing the destruction of humanity's most cherished hopes for expansion beyond our home world. The timeline for recovery could span geological ages. Unlike atmospheric storms or even chemical contamination, orbital debris operates according to the slow but inexorable laws of celestial mechanics. Fragments from Phobos's destruction could continue posing hazards to Mars operations for thousands or even millions of years. Yet even this scenario pales in comparison to the possibility that we're thinking too locally about Atlas's potential for destruction. What if the October 3rd encounter at Mars represents not an endpoint, but merely the first domino in a cascade of gravitational interactions that could ultimately threaten Earth itself? The physics of orbital perturbations operate on timescales that make human planning horizons seem laughably short. A small gravitational nudge today might not manifest as a significant threat until decades or even centuries in the future. As we prepare to explore the chain reaction scenario, we must confront the disturbing possibility that Atlas's brief dance with Mars could set in motion a sequence of events that ultimately brings cosmic disaster to our own doorstep. Part 6. The chain reaction to Earth. Distance, in cosmic terms, provides only the illusion of safety. NASA's current projections place ATLAS at its closest approach to Earth sometime in December 2025, at approximately 1.8 astronomical units, roughly 270 million kilometers away. By any reasonable measure, this represents a comfortable margin that should preclude any direct threat to our home planet. But the solar system operates as an interconnected web of gravitational influences, where the butterfly effect can manifest on planetary scales over extended timelines. What happens at Mars in October doesn't stay at Mars. It propagates outward through the complex gravitational relationships that bind our solar system together, creating ripple effects that can take decades or even centuries to fully manifest. Consider the mathematics of orbital perturbation theory. Every gravitational encounter, no matter how minor, slightly alters the trajectory of every object involved. Atlas's passage near Mars will inevitably change both objects' orbits by tiny amounts, shifts measured in meters per second that seem utterly insignificant in the context of planetary velocities measured in kilometers per second. But those tiny changes accumulate over time through a process known as gravitational resonance. Just as a small push applied at the right moment can set a massive pendulum swinging, small orbital changes can compound over multiple passes through resonant regions of the solar system. What begins as an imperceptible nudge can eventually grow into trajectory changes measured in thousands of kilometers. The most immediate concern involves debris. If Atlas undergoes the kind of fragmentation event we explored in our Mars impact scenario, the resulting fragments won't simply disappear after their encounter with the red planet. Each piece will continue following its own modified orbit through the inner solar system, creating what astronomers euphemistically call a persistent hazard environment. Some of these fragments might find themselves in orbital resonances with Earth's orbit, creating periodic encounters that could persist for decades. Others might be perturbed into highly elliptical paths that bring them into the inner solar system during unpredictable time windows. The result would be a subtle but measurable increase in the background flux of potentially hazardous objects threatening Earth. NASA's planetary defense infrastructure has made remarkable progress in recent years. The Asteroid Terrestrial Impact Last Alert System, PAN-STARS, and the Future Legacy Survey of Space and Time are designed to provide years or even decades of advance warning for most objects large enough to cause regional or global damage on Earth. But these systems were calibrated to detect objects following relatively predictable orbits within our solar system. Atlas fragments, arriving on chaotic trajectories, influenced by interstellar velocities and multiple gravitational encounters, might not fit the standard detection profiles. Their approach angles could be unusual, their velocities unexpected, their composition different enough from typical asteroids to confuse automated classification systems. The timeline for these threats could span generations. Unlike the immediate drama of an impact or atmospheric disruption, gravitational perturbations operate on what physicists call secular timescales, changes that accumulate slowly but inexorably over periods measured in decades or centuries. We might not fully understand the consequences of Atlas's October 3rd encounter with Mars until the 2040s or beyond. This temporal displacement of consequences creates a particularly insidious form of cosmic risk. The politicians and space agency administrators making decisions about planetary defense funding today might not be around to face the consequences of their choices when Atlas-derived fragments begin threatening Earth in the 2050s or beyond. The Yarkovsky effect compounds these concerns in ways that make long-term prediction nearly impossible. This subtle phenomenon occurs when small objects absorb sunlight during the day and re-radiate that heat during the night, creating a tiny but persistent thrust that can significantly alter orbits over extended periods. For fragments of Atlas that might be composed of exotic interstellar materials with thermal properties, unlike anything in our solar system, the Yarkovsky effect could produce orbital evolution that defies all current models. Picture this nightmare scenario unfolding over the next 50 years. Atlas fragments, initially deemed harmless by computer simulations based on conventional asteroid behavior, gradually migrate into Earth-threatening orbits through Yarkovsky drift patterns that no one anticipated. By the time ground-based telescopes detect the threat, there might be insufficient time to organize effective deflection missions. The precedent for such cascading gravitational disasters already exists in our solar system's history. The Late Heavy Bombardment, which occurred approximately 4 billion years ago, may have been triggered by gravitational resonances that destabilize the outer planet's orbits, sending a barrage of comets and asteroids into the inner solar system. The craters on our moon serve as permanent reminders that gravitational chaos can transform peaceful cosmic neighborhoods into shooting galleries. But ATLAS introduces variables that the late heavy bombardment never included: interstellar velocities, exotic compositions, and fragmentation patterns that might not follow the rules established by billions of years of solar system evolution. We're potentially facing a new category of gravitational cascade, one for which our solar system has no historical precedent and our models have no reliable foundation. The meteor shower implications alone could be spectacular in the most ominous sense of that word. Earth regularly encounters debris streams from known comets, producing predictable annual meteor showers that delight amateur astronomers and generally pose no threat beyond the occasional satellite impact. But meteor showers from ATLAS fragments would be fundamentally different beasts. These wouldn't be the gentle light shows of the Perseids or Geminids, where tiny particles burn up harmlessly in Earth's atmosphere. ATLAS fragments, travelling at interstellar velocities and potentially composed of materials that don't behave like conventional meteoroids, could produce airburst events that rival the Tunguska explosion of 1908. The Tunguska event, which flattened 2,000 square kilometers of Siberian forest, resulted from an object estimated to be only 30 to 60 meters in diameter. Now imagine multiple Tunguska-class events occurring as Earth passes through debris streams from ATLAS fragmentation. The cumulative effect could devastate entire continents over periods of decades. Modern civilization's vulnerability to such events has increased exponentially since 1908. Our power grids, communication networks, and transportation systems create cascade failure points that didn't exist during the Tunguska era. A single airburst event over a major metropolitan area could trigger economic and social disruptions that persist for years. The insurance industry has already begun grappling with the implications of increased cosmic risk. Lloyd's of London and other major insurers have been quietly developing models for space weather events that could affect global commerce. But their current risk assessments assume that potentially hazardous objects will be detected years in advance, allowing for orderly evacuations and infrastructure hardening. ATLAS fragments following chaotic, unpredictable orbits could arrive with much shorter warning times, potentially catching both emergency management systems and insurance markets completely unprepared. The economic implications could dwarf the immediate physical damage, creating a death corridor of elevated cosmic risk that persists for decades. Perhaps most unsettling is the possibility that we're already committed to this future cascade, regardless of what actually happens on October 3rd. The gravitational perturbations that will ultimately determine ATLAS's long-term influence on inner solar system dynamics may have already been set in motion by earlier phases of the comet's approach. Orbital mechanics operates according to deterministic chaos, systems where tiny initial differences can produce dramatically different outcomes, but where those outcomes are nevertheless inevitable once the initial conditions are established. We may be living through the early stages of a gravitational cascade that was predetermined when ATLAS first entered our solar system months ago. The monitoring systems that might provide early warning of developing threats face their own vulnerabilities in an era of increasing cosmic chaos. Ground-based telescopes can be affected by atmospheric conditions. Space-based observatories can be damaged by the same debris fields they're designed to detect. Communication systems that relay threat assessments to planetary defense networks could be disrupted by the electromagnetic chaos we explored in our Mars atmospheric scenario. But even if our detection systems function flawlessly, even if we spot every ATLAS fragment decades before it threatens Earth, we face the sobering reality that deflection technology remains largely theoretical. The DART mission successfully demonstrated that we can alter an asteroid's trajectory, but only under carefully controlled conditions, involving a known target with predictable composition and orbital characteristics. ATLAS fragments, with their exotic interstellar origins and chaotic post-fragmentation orbits, might not respond to deflection attempts in the ways our models predict. We could find ourselves in the position of knowing exactly when and where a cosmic catastrophe will occur, but being powerless to prevent it. This is the true horror of the chain reaction scenario. Not the immediate spectacle of planetary destruction, but the slow-motion catastrophe of watching our cosmic neighborhood become increasingly hazardous over timescales that exceed human political and economic planning horizons. We might be witnessing the beginning of humanity's first self-inflicted cosmic crisis, triggered by our own expansion into a solar system that was never as stable as we assumed. Yet, even as we contemplate these terrestrial nightmares, we must acknowledge that our robotic emissaries currently orbiting Mars face more immediate existential threats. The spacecraft that represent our eyes and ears at the Red Planet operate according to engineering principles that never anticipated encounters with interstellar chaos. What happens when cutting-edge space technology meets cosmic forces that follow no earthly rules? Part 7. Spacecraft at Risk. Space, despite its romantic portrayal in science fiction, remains fundamentally hostile to the delicate electronic systems that extend human presence beyond Earth's protective embrace. Our spacecraft represent triumphs of engineering precision, complex assemblages of sensors, processors, and communication systems that must function flawlessly in environments where the smallest failure can mean mission death. Mars orbit presents unique challenges that push spacecraft design to its absolute limits. The radiation environment, while less intense than Jupiter's murderous magnetic field, still degrades electronic components over time. Micrometeoroid impacts, though infrequent, can disable critical systems with surgical precision. Temperature extremes cycle between the frigid cold of Martian shadow and the intense heat of unfiltered sunlight, causing thermal stresses that gradually fatigue even the most robust materials. But the engineers who designed our current Mars fleet, the Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, never anticipated having to operate in the chaotic environment that Atlas's passage might create. These spacecraft were built to study Mars under normal conditions, not to survive cosmic catastrophes. Consider the vulnerabilities inherent in modern spacecraft architecture. High-voltage power systems, essential for operating sophisticated instruments across the vast distances of interplanetary space, become liabilities when exposed to the kind of electromagnetic chaos that Atlas could generate. Static electricity buildup from charged particle bombardment can create voltage differentials that arc across circuit boards, instantly destroying components that took years to design and test. The Mars Reconnaissance Orbiter, launched in 2005, carries some of the most sophisticated imaging and communication equipment ever deployed in Mars orbit. Its high-rise camera can resolve features smaller than a meter across on the Martian surface, while its radio science experiments probe the planet's atmospheric structure with unprecedented precision. But this technological marvel depends on star trackers, optical sensors that maintain spacecraft orientation by observing known stellar positions. A debris field from Atlas fragmentation could render these star trackers useless by creating false targets or overwhelming their sensitive photodetectors with unexpected light sources. Without reliable attitude control, the Mars Reconnaissance Orbiter's high-gain antenna couldn't maintain its precise pointing toward Earth, severing the communication link that allows the spacecraft to transmit its scientific discoveries back to mission control. MAVEN, the Mars Atmosphere and Volatile Evolution mission, faces different but equally severe challenges. This spacecraft was specifically designed to study how solar-wind interactions strip away Mars's upper atmosphere. Its particle detectors and magnetometers are calibrated to measure the gentle, predictable flow of charged particles from our Sunday. But Atlas's passage could flood MAVEN's sensors with particle fluxes orders of magnitude higher than anything they were designed to handle. Like trying to measure a gentle breeze with an instrument suddenly exposed to a hurricane, MAVEN's delicate sensors could be permanently damaged or saturated beyond their ability to provide meaningful data. The electromagnetic pulse effects, while not equivalent to the fictional EMP weapons of Hollywood thrillers, could still induce damaging currents in spacecraft wiring systems. Modern spacecraft carry thousands of meters of electrical cables, creating efficient antennas for capturing electromagnetic energy from external sources. A sudden surge in the local electromagnetic environment could turn these essential connections into conduits for destructive electrical currents. Each spacecraft also carries its own unique vulnerabilities based on mission-specific design choices. Mars Express, the European Space Agency's veteran Mars explorer, has been operating since 2004 and shows signs of age in several subsystems. Components that were already operating near their design limits might not survive additional stresses from an unexpectedly chaotic electromagnetic environment. The Trace Gas Orbiter represents our most recent addition to the Mars fleet, equipped with state-of-the-art spectrometers designed to detect trace gases in the Martian atmosphere, including potential biosignatures that could indicate past or present life. But these ultra-sensitive instruments require extraordinarily stable operating conditions to distinguish genuine atmospheric signals from instrumental noise. The chaotic electromagnetic environment created by ATLAS's passage could overwhelm these sensitive measurements with false signals, rendering months or even years of observations scientifically worthless. Even worse, electromagnetic interference could damage the spectrometer's calibration systems, requiring complex recalibration procedures that might not be possible to execute remotely. But let's escalate this scenario to its most catastrophic logical conclusion. What if ATLAS's passage doesn't just threaten individual spacecraft, but creates systemic failures across the entire Mars orbital infrastructure? What if the electromagnetic chaos proves severe enough to trigger a cascade of safe-mode shutdowns that effectively blinds humanity's robotic presence at Mars? Spacecraft designers incorporate safe-mode systems as a last resort for preserving mission capability when sensors detect anomalous conditions. In safe mode, all non-essential systems shut down, solar panels orient toward the Sun for maximum power generation, and the spacecraft waits for commands from Earth to assess damage and attempt recovery. But safe mode assumes that the anomalous conditions are temporary, and that ground controllers will eventually be able to re-establish communication to begin recovery procedures. If ATLAS creates electromagnetic chaos that persists for weeks or months, our Mars orbiters could find themselves trapped in safe mode for extended periods, unable to conduct science operations or even relay communications from surface rovers. The psychological impact on Mars exploration programs would be devastating. Imagine the public reaction to news that all of our Mars orbiters have gone silent simultaneously. Social media would explode, with conspiracy theories about cosmic catastrophes and government cover-ups. The carefully cultivated public support for Mars exploration, built up over decades of successful missions and stunning imagery, could evaporate overnight. Mission controllers at JPL and other space agencies would face an unprecedented crisis management challenge. Standard spacecraft recovery procedures assume that you can communicate with the affected vehicle to diagnose problems and upload corrective commands. But if electromagnetic interference prevents reliable communication, ground controllers might find themselves essentially helpless to assist their distant robotic charges. The ripple effects would extend to Mars surface operations as well. The Perseverance and Curiosity rovers depend on orbital relay assets to maintain regular communication with Earth. Without these relay systems, the rovers would be forced to communicate directly with Earth using their own lower power radio systems, a process that severely limits data transmission rates and operational flexibility. Even more troubling is the possibility that ATLAS could trigger the kind of rare solar space weather coupling event that space physicists have been warning about for decades. If the comet's passage coincides with a major solar energetic particle event or coronal mass ejection, the combined effects could overwhelm spacecraft shielding systems that were designed to handle either threat individually, but not both simultaneously. The recovery timeline for such a cascading failure could span years. Unlike terrestrial infrastructure, which can be repaired by sending technicians to the affected location, spacecraft failures in Mars orbit require complex troubleshooting procedures conducted across interplanetary distances, with communication delays measured in minutes. Some spacecraft might never recover from the electromagnetic trauma of ATLAS's passage. Components damaged by electrical surges or degraded by prolonged exposure to charged particle bombardment might simply fail to respond to recovery attempts. Missions that have successfully operated for decades could end abruptly, not from the gradual aging of their systems, but from sudden exposure to cosmic forces that overwhelm their design parameters. The loss of Mars orbital assets would set back our understanding of the Red Planet by years or possibly decades. Scientific investigations that depend on long-term monitoring would be interrupted just as they were beginning to reveal crucial insights about Martian climate evolution, atmospheric chemistry, and geological processes. But perhaps most ominously, the failure of our Mars spacecraft fleet would leave us blind to whatever Atlas actually does to the red planet itself. We might find ourselves in the position of knowing that something significant happened at Mars, but being unable to observe or understand the consequences until new missions can be designed, built, and launched, a process that typically requires at least a decade. Yet even as we contemplate these technological nightmares, we must remember that Atlas operates in the realm of solar system dynamics, where even our sun can be influenced by sufficiently dramatic cosmic events. What if the October 3rd encounter represents not just a threat to Mars and its artificial satellites, but the beginning of a solar weather catastrophe that could affect every planet in our cosmic neighborhood? Part 8. Radiation storms and solar chaos. The Sun, for all its apparent constancy, operates as a barely controlled fusion reactor, balanced on the knife's edge between stellar stability and explosive chaos. Solar activity follows 11-year cycles that can unleash electromagnetic storms capable of disrupting technology across the entire solar system. But these natural solar tantrums pale in comparison to what might happen if Atlas's passage through the inner solar system coincides with peak solar activity. Atlas's perihelion, its closest approach to our star, occurs in late October 2025 at approximately 1.4 astronomical units from the sunday. While this distance keeps the comet safely outside the realm of the dramatic sun grazers that occasionally plunge directly into our star's corona, it places Atlas well within the region where solar-wind interactions can become intense and unpredictable. The physics of comet-solar-wind interaction follow well-established principles under normal circumstances. As a comet approaches the Sun, solar radiation vaporizes its surface materials, creating the characteristic coma and tail that make these objects visible from Earth. The solar wind, a stream of charged particles flowing outward from the Sun at speeds exceeding 400 kilometers per second, shapes these emissions into the distinctive anti-sunward pointing tails that have inspired human imagination for millennia. But Atlas isn't a normal comet operating under normal circumstances. Its massive carbon dioxide coma and erratic brightness variations suggest internal processes that don't match our standard models of cometary behavior. When an object following non-standard patterns encounters the complex electromagnetic environment near the Sun, the results can be genuinely unpredictable. Consider what happens when Atlas's ion tail, a stream of electrically charged particles accelerated by the solar wind, extends millions of kilometers into space during the comet's perihelion passage. This tail doesn't exist in isolation. It interacts with the solar wind, with the Sun's magnetic field, and potentially with other electromagnetic phenomena in ways that could create feedback loops affecting solar activity itself. The Sun's magnetic field lines extend throughout the solar system in complex patterns that astronomers are still trying to fully understand. When a massive ion stream from Atlas intersects these field lines, it could theoretically create perturbations that propagate back toward the Sun, potentially triggering enhanced solar activity in regions that might otherwise remain quiet. Now, let's escalate this scenario to its most alarming possible conclusion. What if Atlas's perihelion passage occurs during a period when the Sun is already approaching peak activity in its natural cycle? What if the electromagnetic perturbations from the comet's ion tail arrive at our star just as solar magnetic field lines are becoming unstable and primed for explosive release? The result could be a solar energetic particle event of unprecedented magnitude, a cosmic storm that makes the Carrington event of 1859 look like a gentle spring shower. The Carrington event, caused by a relatively modest coronal mass ejection, was powerful enough to disrupt telegraph systems across North America and Europe, creating auroras visible as far south as the Caribbean. But that 19th century solar storm occurred during an era when human civilization had minimal dependence on electrical infrastructure. A Carrington-class event today would cripple power grids, satellite networks, and communication systems across multiple continents. The economic damage would be measured in trillions of dollars, and the recovery time could span years. An Atlas-enhanced solar storm could be orders of magnitude more severe. The charged particles accelerated by such an event would arrive at Earth, traveling at significant fractions of the speed of light carrying energies that would overwhelm even hardened satellite systems and potentially damage components of terrestrial power grids despite their protective shielding. The space weather monitoring systems that provide advance warning of solar storms, SOHO, the Geostationary Operational Environmental Satellites, and the Deep Space Climate Observatory would themselves be at risk from the very phenomena they're designed to detect. If these early warning systems are damaged or destroyed by the initial wave of comet-charged particles, subsequent waves could arrive at Earth with little or no advance notice. The cascade effects on modern civilization would be catastrophic beyond anything in human experience. GPS navigation systems would fail as satellites lose their ability to maintain precise timing. The internet backbone, dependent on precisely synchronized data transmission protocols, would fragment as timing references disappear. Air traffic control systems would revert to visual flight rules as radar systems succumb to electromagnetic interference. But Earth wouldn't be the only planet affected by such a solar catastrophe. Mars, already facing potential chaos from Atlas's direct passage, would find itself bombarded by charged particles energetic enough to strip away significant portions of its already tenuous atmosphere. The radiation levels at the Martian surface would spike to levels that would be immediately lethal to any human explorers unfortunate enough to be present. The moons of Jupiter and Saturn, normally protected from the worst solar storms by their planets' powerful magnetic fields, could experience radiation doses that sterilize their surfaces to depths measured in meters. Europa and Enceladus, prime targets in the search for extraterrestrial life, might find their subsurface oceans bombarded with enough radiation to destroy any biological processes that might have been occurring there. Perhaps most disturbing is the possibility that an Atlas-triggered solar storm could create a feedback loop that persists long after the comet has departed the inner solar system. Solar magnetic field disruptions can take months or even years to fully stabilize, during which time our star could continue producing enhanced particle emissions that threaten technological civilization across multiple planets. The historical record provides little guidance for managing such a scenario, because no similar event has occurred during the era of space-age technology. The best solar storm data we have comes from ice core analyses and tree ring studies that suggest periodic episodes of enhanced solar activity throughout Earth's history. But these natural archives tell us nothing about the specific mechanisms or timelines involved. Space weather prediction models, sophisticated as they are, weren't designed to account for the additional variables introduced by interstellar comets interacting with solar magnetic fields. The computer simulations that space weather forecasters rely on might prove completely inadequate for predicting the behavior of an Atlas-enhanced solar storm. The policy implications alone would be staggering. How do you prepare modern technological civilization for a phenomenon that might occur with little warning and could persist for months? How do you maintain emergency services when the communication systems they depend on might be the first casualties of electromagnetic chaos? How do you prevent social collapse when the just-in-time supply chains that feed modern cities depend on GPS navigation and electronic payment systems that could fail simultaneously? International cooperation, already strained by terrestrial political conflicts, would be essential for managing a global space weather catastrophe. But the same electromagnetic chaos that threatens technological systems could also disrupt the communication networks that international coordination depends on. We might find ourselves facing a planetary emergency while simultaneously losing the ability to coordinate our response efforts. Yet even as we contemplate these electromagnetic nightmares, we must remember that Atlas might be delivering more than just charged particles and magnetic field disruptions to the inner solar system. What if the comet's passage doesn't just threaten our technology, but fundamentally alters the chemical environment of planets in ways that could affect their long-term habitability? What if Atlas's true legacy isn't measured in immediate destruction, but in subtle chemical changes that accumulate over decades? Part 9. Terraforming by disaster. The concept of terraforming Mars, transforming the red planet into a world suitable for human habitation, has captivated scientists and science fiction writers for decades. Most proposals involve gradual, carefully controlled processes spanning centuries, releasing greenhouse gases to thicken the atmosphere, melting polar ice caps to create bodies of liquid water, introducing extremophile organisms to begin establishing biological cycles. But what if Atlas accomplishes a form of terraforming through cosmic accident, not the gradual, beneficial transformation we've envisioned, but a rapid, chaotic alteration that makes Mars even less hospitable to human life than it already is? The massive carbon dioxide emissions from Atlas's coma represent a chemical payload of staggering proportions. Spectroscopic analysis suggests that the comet is venting CO2 at rates that dwarf anything previously observed in our solar system. While most of this material will miss Mars entirely and continue into interplanetary space, even a small fraction could represent millions of tons of additional greenhouse gases entering the Martian system. Under normal circumstances, this might sound beneficial for terraforming efforts. Carbon dioxide, after all, is the primary greenhouse gas that most Mars terraforming proposals plan to introduce to thicken the planet's atmosphere and raise surface temperatures. Additional CO2 from Atlas might seem like a head start on humanity's eventual climate engineering projects, but the devil, as always, lurks in the details of planetary atmospheric chemistry. Mars's current atmospheric system exists in a delicate equilibrium that has persisted for millions of years. Sudden chemical inputs, even of gases that already exist in the atmosphere, can trigger cascading reactions that destabilize established patterns in unpredictable ways. Atlas's carbon dioxide isn't arriving through the gradual, controlled processes that terraforming engineers envision. Instead, it's being delivered as a chaotic surge, coinciding with electromagnetic disruptions, possible debris impacts, and dust storm activity that could fundamentally alter how the gas interacts with existing atmospheric chemistry. Consider the albedo effects alone. Mars's reddish surface reflects sunlight in ways that help maintain the planet's current temperature regime, but Atlas's passage could deposit significant quantities of dark, organic-rich dust across large portions of the planetary surface. This dust, composed of materials that formed in an alien stellar environment, might have thermal absorption characteristics completely unlike anything currently on Mars. Dark surfaces absorb more heat than light surfaces, a basic physical principle that could trigger runaway heating in regions where Atlas dust accumulates. Local temperature spikes could vaporize subsurface water ice, adding water vapor to an atmosphere that's already struggling to maintain chemical equilibrium. The additional moisture could interact with Atlas's carbon dioxide in ways that create acid rain conditions, further altering surface chemistry. But here's where the scenario becomes genuinely nightmarish from a terraforming perspective. What if Atlas's chemical contributions don't make Mars more Earth-like, but instead push the planet toward a Venus-like greenhouse catastrophe? Venus, despite being similar to Earth in size and composition, experienced a runaway greenhouse effect that transformed it into a hell world, with surface temperatures hot enough to melt lead and atmospheric pressures crushing enough to destroy spacecraft within hours. Mars, with its lower gravity and greater distance from the Sun, shouldn't be susceptible to Venus-style greenhouse runaway under normal circumstances. But Atlas introduces variables that have never been tested in planetary climate models. Exotic, organic, compounds from interstellar space might catalyze chemical reactions that amplify greenhouse warming beyond what pure CO2 additions would suggest. The timeline for such changes could be measured in years, rather than the geological timescales typically associated with natural climate evolution. Planetary atmospheres, when pushed beyond critical thresholds, can undergo rapid transitions that completely alter their character within decades. What begins as a modest enhancement of Mars's existing greenhouse effect could accelerate into irreversible atmospheric transformation. Future Mars missions, planned under the assumption that the planet's environment will remain relatively stable and predictable, could find themselves operating in conditions that bear no resemblance to current models. Life support systems designed for Mars's current atmospheric composition might fail catastrophically when confronted with the altered chemistry that Atlas leaves behind. In situ resource utilization, the cornerstone technology that makes long-term Mars habitation economically feasible, depends on being able to extract water, oxygen, and even rocket fuel from the Martian environment using known chemical processes. But if Atlas fundamentally alters the planet's chemical inventory, these ISRU systems might become useless or even dangerous to operate. Imagine astronauts arriving at Mars in the 2030s, only to discover that their atmospheric processors can't function in the chemically altered environment that Atlas created. Instead of producing breathable air, the systems might generate toxic compounds that could poison entire habitats. Water extraction systems might encounter organic contaminants that render the recovered water unsafe for human consumption, despite sophisticated purification efforts. The psychological impact on humanity's space colonization dreams would be devastating. Mars represents our nearest feasible backup planet, our insurance policy against existential risks that could threaten Earth-based civilization. To discover that an interstellar visitor has rendered Mars uninhabitable, just as we're developing the technology to establish permanent settlements, there would be like watching our species' long-term survival prospects evaporate in real time. But the changes Atlas brings to Mars might not be limited to atmospheric and surface chemistry. The comet's passage could alter the planet's electromagnetic environment in ways that affect everything from aurora displays to the behavior of dust storms. Mars's weak magnetic field provides minimal protection against charged particles, making the planet exquisitely sensitive to changes in the local space weather environment. Enhanced electromagnetic activity could affect the Martian ionosphere in ways that interfere with radio communications for decades. Future Mars missions might find themselves operating in a communications environment that requires completely different technologies from those currently being developed. The reliable communication windows that mission planners take for granted might become sporadic and unpredictable. The dust storm implications alone could reshape Mars exploration strategies for generations. If Atlas's electromagnetic effects make global dust storms more frequent or more intense, the reliable solar power that most Mars missions depend on could become unreliable. Nuclear power sources, currently viewed as optional for Mars missions, might become essential for any long-term operations. Perhaps most unsettling is the possibility that we won't fully understand Atlas's impact on Mars until decades after the October 3rd encounter. Atmospheric chemistry operates on timescales that can make immediate assessment impossible. Chemical reactions initiated by Atlas's passage might continue occurring for years, gradually altering Mars's environment in ways that won't become apparent until future missions attempt to operate in the changed conditions. The terraforming disaster scenario forces us to confront an uncomfortable truth about planetary engineering. We don't understand planetary atmospheres well enough to predict how they'll respond to sudden, large-scale chemical inputs. Our models work reasonably well for gradual changes occurring over geological timescales, but they've never been tested against the kind of cosmic chemical shock that Atlas might deliver. Yet even as we contemplate these environmental nightmares, we must acknowledge that the most insidious effects of Atlas's passage might not be physical at all. What if the October 3rd encounter unfolds exactly as predicted by official models, with no dramatic impacts, no electromagnetic chaos, no chemical catastrophes, but the public refuses to believe that nothing significant occurred? What if the real disaster is informational rather than physical? Part 10. The Don't Look Up Angle. Information, in the modern age, flows according to its own chaotic dynamics that can be more unpredictable than orbital mechanics and more dangerous than cosmic radiation. When significant astronomical events occur, the gap between scientific reality and public perception can widen into chasms that swallow rational discourse entirely. Atlas's October 3rd encounter with Mars presents a perfect storm of conditions for informational catastrophe. The event occurs during a solar conjunction period when Earth-based observations are limited. The scientific data requires weeks or months of analysis before meaningful conclusions can be drawn. Most critically, the encounter involves an interstellar object whose behavior doesn't match established patterns, a cosmic wildcard that feeds speculation far more readily than it provides definitive answers. NASA and the European Space Agency have been conspicuously measured in their public communications about Atlas. Official statements acknowledge the unusual nature of the object and confirm plans for observational campaigns during the Mars encounter, but they stop short of providing the kind of dramatic imagery and speculative scenarios that capture public imagination. This cautious approach, while scientifically appropriate, creates an information vacuum that alternative narratives rush to fill. Social media algorithms, designed to maximize engagement rather than accuracy, amplify the most dramatic and alarming interpretations of incomplete data. By the time official scientific analysis is complete, public opinion may be so thoroughly shaped by misinformation that factual corrections become ineffective. The precedent for astronomical misinformation campaigns offers little comfort for those hoping rational discourse will prevail. The 2021 UAP disclosures by the US government demonstrated how quickly speculation can outpace official information when dealing with phenomena that challenge conventional understanding. Congressional hearings that were intended to provide transparency instead generated more questions than answers, feeding conspiracy theories rather than resolving them. ATLAS presents an even more complex challenge because the object is genuinely anomalous in ways that resist simple explanation. Its massive carbon dioxide coma, erratic brightness variations, and exotic orbital characteristics provide just enough genuine mystery to make even outlandish theories seem plausible to non-experts. The delayed release schedule for scientific data compounds the problem. The James Webb Space Telescope's infrared observations of ATLAS, conducted in August, remain under analysis by research teams who follow peer review protocols that prioritize accuracy over speed. Preliminary results might not be publicly available until months after the October 3rd encounter, creating a prolonged period when speculation operates without factual constraints. Meanwhile, amateur astronomers and citizen science groups are conducting their own observations with equipment that, while impressive for backyard use, lacks the sensitivity and calibration of professional observatory instruments. Their images and measurements, shared instantly across social media platforms, may contain artifacts or misinterpretations that professional astronomers would immediately recognize, but that appear compelling to general audiences. The don't look up scenario emerges when this combination of factors creates conditions where the public believes something catastrophic has occurred at Mars, regardless of what actually happened. If ATLAS's encounter produces any unusual phenomena, even relatively minor events that fall well within the range of natural variation, they could be interpreted as evidence of cosmic catastrophe. Picture this nightmare timeline. ATLAS passes Mars on October 3rd with minimal fanfare, producing subtle changes in the planet's electromagnetic environment that require sophisticated analysis to detect. Mars orbiters continue functioning normally but implement precautionary safe mode protocols that temporarily reduce science operations. Surface rovers experience brief communication interruptions as ionospheric conditions fluctuate. From a scientific perspective, this represents an interesting but non-catastrophic encounter that provides valuable data about interstellar object interactions with planetary magnetospheres. But from a public information perspective, it could be interpreted as evidence of deliberate information suppression. The temporary reduction in Mars imagery transmission creates a blackout that conspiracy theorists interpret as evidence that something terrible has occurred. The technical explanations provided by space agencies, detailed discussions of ionospheric propagation effects and spacecraft operating procedures sound like bureaucratic doubler talk to audiences primed to expect dramatic revelations. Social media fills with increasingly elaborate theories about what really happened during the ATLAS encounter. Computer-generated images purporting to show Mars impact craters circulate faster than official corrections can be issued. Amateur radio operators claim to have intercepted emergency transmissions from Mars orbiters that space agencies refuse to acknowledge. The psychological dynamics that drive such information cascades are well understood by cognitive scientists but remain poorly addressed by official communication strategies. When people are primed to expect dramatic events, normal scientific caution is interpreted as evasion. When official explanations involve technical details that require specialized knowledge to understand, they're dismissed as attempts to obscure rather than illuminate. The 2024 presidential election demonstrated how quickly misinformation can reshape public perception of reality. The same psychological mechanisms that allowed unfounded claims about election fraud to persist despite overwhelming factual evidence could easily be applied to claims about cosmic cover-ups and suppressed astronomical data. Congressional oversight of space agencies, intended to ensure transparency and accountability, could actually amplify misinformation if representatives without scientific training demand answers to questions that can't be answered definitively with available data. Hearings that feature dramatic testimony about potential cosmic threats could generate media coverage that treats speculation as established fact. The international dimension adds another layer of complexity to information management. The European Space Agency, with its different communication protocols and political constraints, might release information on schedules that don't align with NASA's plans. These timing differences could be interpreted as evidence of coordination failures or deliberate information management, rather than routine operational considerations. Amateur astronomers in countries with different transparency traditions might share observations that contradict or complicate official narratives. Chinese or Russian space agencies, operating under different political pressures, might characterize the same events in ways that seem inconsistent with Western scientific agencies' interpretations. The cumulative effect could be a global information environment where multiple contradictory versions of what really happened at Mars compete for public attention, with scientific accuracy becoming just one variable among many in determining which narratives gain traction. But perhaps most insidiously, the don't look up scenario could become self-fulfilling if public pressure forces a premature disclosure of preliminary scientific results that later prove incorrect. Space agencies, facing congressional inquiries and media scrutiny, might feel compelled to release tentative findings that satisfy public demand for information but lack the rigorous analysis needed for scientific accuracy. These premature disclosures, when later corrected by more complete analysis, could be interpreted as evidence of incompetence or deliberate deception rather than normal scientific process. The correction cycle, where initial dramatic claims are gradually moderated by more careful analysis, mirrors the pattern that fuels conspiracy theories about government cover-ups. The long-term consequences for space science could be severe. Public trust in space agencies, built up over decades of successful missions and stunning discoveries, could be damaged by information management failures during the Atlas encounter. Future missions might face skeptical audiences who've been conditioned to doubt official explanations of astronomical phenomena. Yet even as we contemplate these informational nightmares, we must prepare for the possibility that October 3rd will pass without providing clear resolution to any of the questions Atlas has raised. What happens when the most significant astronomical event of our generation occurs and leaves us with more mysteries than answers? What happens when the universe refuses to provide the dramatic closure that human psychology demands? Part 11. If Mars takes the hit. October 3rd, 2025, the day Mars died. Not in the literal sense, of course. Planets don't die the way living creatures do. They don't take final breaths or fade peacefully into cosmic night. But on this date, Mars as we've known it, humanity's next frontier, our red-hued beacon of hope, ceased to exist as a destination for human exploration. The impact occurred at 1400 hours Universal Time, as Atlas Fragment Designation AF7 slammed into Mars's northern hemisphere at a velocity that made bullets look sluggish. The object, roughly 400 meters in diameter and composed of exotic ices and organic compounds that had never existed anywhere in our solar system, delivered the kinetic energy equivalent of several thousand nuclear weapons to a planet utterly unprepared for such cosmic violence. Within minutes, the Mars Reconnaissance Orbiter's cameras captured images that would haunt planetary scientists for generations. An expanding fireball that briefly outshone the sun in Mars's pale sky, followed by a shock wave that raced across the planet's surface at hypersonic speeds, obliterating everything in its path. The crater, when the dust finally settled enough for orbital reconnaissance, measured 37 kilometers across, a wound in Mars's ancient surface that exposed rock formations that hadn't seen daylight since the planet's youth. But the crater was merely the beginning of Mars's transformation into an alien world. The impact had excavated millions of tons of subsurface permafrost, instantly vaporizing water ice that had been locked in Mars's crust for billions of years. This sudden injection of water vapor into the thin Martian atmosphere created weather patterns that defied every model in the climatology textbooks. Massive storm systems, driven by temperature differentials that had never existed in Mars's recorded history, began forming within hours of the impact. The electromagnetic pulse generated by the collision overwhelmed every piece of human technology in Mars orbit simultaneously. The Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, humanity's electronic eyes at the Red Planet, all triggered emergency safe mode protocols as their star trackers lost lock and their communication systems were flooded with radio frequency interference from the ionized debris cloud. But safe mode protocols assume that anomalous conditions are temporary. They're designed to protect spacecraft during brief periods of uncertainty, not during planetary catastrophes that fundamentally alter the electromagnetic environment for months or years. One by one, as backup power systems depleted and critical components failed under conditions they were never designed to handle, the orbiters fell silent. The communication blackout with Mars lasted 14 months. For over a year, humanity had no direct contact with the red planet that had captivated our imagination for centuries. The rovers, Perseverance, Curiosity, and the international collection of landers that had been studying Mars's geology and climate vanished into radio silence. Mission controllers at JPL, normally accustomed to receiving daily reports from their robotic charges, found themselves staring at blank screens and dead communication channels. The psychological impact on Earth was immediate and profound. Mars represented humanity's next chapter, our cosmic coming-of-age story. To watch it disappear from our technological grasp was like witnessing the destruction of our species' most cherished dreams. Stock markets plunged as aerospace companies saw their Mars exploration contracts evaporate overnight. Congressional hearings demanded answers that no one could provide. When communication was finally re-established through emergency protocols and hastily launched replacement satellites, the Mars that emerged from the radio silence bore little resemblance to the world we thought we knew. The planet's entire atmospheric circulation pattern had been disrupted by the impact. What had been a relatively predictable climate system, with seasonal dust storms and well-understood weather patterns, had become chaotic and unpredictable. Global dust storms, once rare events that occurred every few Martian years, became the new normal. The planet's surface remained shrouded in a persistent veil of suspended particles that blocked sunlight and made solar power unreliable for any surface operations. Temperatures plummeted as the dust-laden atmosphere reflected incoming solar radiation back into space, triggering a nuclear winter effect that persisted for over 3 Martian years. The radiation environment around Mars had been permanently altered by the impact. The collision had not only lofted radioactive materials from deep within Mars's crust, but had also created a temporary debris ring around the planet, a chaotic collection of impact ejecta that bombarded the upper atmosphere for months, creating persistent auroral displays and ionospheric disturbances that made radio communication sporadic and unreliable. Phobos, Mars's larger moon, suffered collateral damage that sealed the fate of any future human missions to Mars. Impact debris from the surface collision had struck the irregularly shaped moon with sufficient force to destabilize its already precarious orbit. Instead of the gradual 50 million year death spiral that astronomers had predicted, Phobos began fragmenting immediately, creating a debris field that would plague Mars' orbit for centuries to come. The chunks of Phobos, ranging in size from boulders to building-sized fragments, followed chaotic orbits that made navigation through Mars's orbital space a deadly game of cosmic roulette. Any spacecraft attempting to reach Mars would have to thread its way through a 3-dimensional minefield of rocky debris, moving at speeds that would turn even small collisions into catastrophic events. The dreams of Mars colonization, which had seemed tantalizingly close to reality in the early 2020s, evaporated in the radioactive dust clouds that now permanently shrouded the red planet. The carefully planned Artemis Mars missions were cancelled indefinitely. The international Mars exploration treaties became obsolete overnight, as the planet they were designed to govern became too dangerous to visit. Private space companies that had invested billions in Mars transportation systems found their business models destroyed by cosmic accident. SpaceX's Starship, designed specifically for Mars cargo delivery, was hastily repurposed for lunar missions and asteroid mining operations. Blue Origin's Mars landing systems became museum pieces before they ever flew. The scientific community struggled to comprehend the magnitude of what had been lost. Mars had been our natural laboratory for studying planetary evolution, climate change, and the possibility of life beyond Earth. The rovers and landers that had spent decades carefully analyzing Martian soil samples were now buried under meters of radioactive debris, their discoveries forever lost to the cosmic catastrophe. But perhaps the most devastating realization was temporal. The Mars that Atlas had destroyed was irreplaceable on human timescales. Planetary atmospheres can recover from major disruptions, but the process typically requires millions of years. The Mars that might eventually emerge from the chaos Atlas had created would be fundamentally different from the world that had beckoned to human explorers for generations. The impact had altered Mars's axial tilt slightly, changing the planet's seasonal patterns in ways that would take decades to fully understand. The massive injection of water vapor and exotic organic compounds from Atlas's nucleus had initiated atmospheric chemistry that followed no terrestrial models. This wasn't the gradual terraforming that scientists had envisioned. It was rapid, chaotic, planetary transformation that rendered all previous Mars exploration plans obsolete. The ripple effects extended far beyond Mars itself. The destruction of humanity's most accessible stepping stone to the outer solar system forced a complete recalculation of our species' expansion into space. Instead of using Mars as a staging area for missions to the asteroid belt and the moons of Jupiter, space agencies were forced to develop more complex and expensive direct routes to these destinations. The psychological trauma of watching our cosmic neighbor become uninhabitable created a generation of space scientists who viewed interstellar objects with suspicion rather than wonder. The romantic notion of comets as harbingers of cosmic beauty was replaced by a pragmatic understanding that the universe contains forces capable of destroying worlds without notice or malice. Congressional funding for planetary defense programs increased dramatically as the reality of cosmic threats became undeniable. The DART mission's success in deflecting asteroid Dimorphos, once viewed as an interesting technology demonstration, suddenly became the foundation for a multi-billion-dollar planetary protection initiative designed to prevent future Atlas-scale disasters. Yet even as humanity mourned the loss of Mars as a destination, we began to understand that the October 3rd disaster might have revealed something even more troubling about our cosmic neighborhood. If Atlas could destroy Mars through a chance encounter, what other interstellar visitors might be silently approaching our solar system, carrying the potential for even greater catastrophes? The monitoring networks established to track near-Earth asteroids were hastily expanded to detect interstellar objects years before their closest approaches to populated worlds. The assumption that space was mostly empty and safe, was replaced by a sobering recognition that the universe was full of wandering objects capable of altering or destroying planets on timescales far shorter than geological processes. But as we contemplate this alternate history where Mars died on October 3rd, we must remember that the universe rarely provides such dramatic closure to cosmic mysteries. What if Atlas's encounter with Mars proves to be far more subtle and enigmatic than either our worst fears or our wildest speculations suggest? What if October 3rd passes quietly, leaving us with more questions than answers about our cosmic vulnerability? Part 12. If Mars survives. October 3rd came and went like a cosmic whisper, rather than a scream. The European Space Agency's final trajectory calculations placed Atlas at its closest approach to Mars, 30.2 million kilometers, at precisely 11 hours, 17 minutes, universal time. No impacts occurred, no electromagnetic storms materialized, no global dust tempests engulfed the red planet in radioactive chaos. Mars continued its ancient orbit around the Sun, apparently unperturbed by its brush with interstellar visitor Atlas. The first official statement came from ESA Mission Control 6 hours after closest approach. 3I-ATLAS has completed its Mars encounter within all predicted parameters. Mars orbital assets report normal operations, no anomalous activity detected at this time, further analysis pending. 42 words that somehow managed to sound both reassuring and deeply unsatisfying. Within minutes of the release, social media platforms erupted with a collective expression of anticlimax that bordered on indignation. "That's it?" became the most trending phrase on Twitter within an hour. Reddit forums dedicated to Atlas speculation descended into bitter debates about whether the boring outcome represented successful scientific prediction or evidence of a coordinated cover-up. The public reaction revealed something profound about human psychology and our relationship with cosmic events. For months, ATLAS had captured global attention precisely because it represented the unknown, the potentially catastrophic, the cosmically significant. Its mysterious behavior and interstellar origins had fed speculations that ranged from scientifically plausible to utterly fantastic, but all of them shared a common assumption: that something dramatic would occur when this alien visitor reached its closest approach to Mars. The reality of cosmic encounters, however, rarely matches human expectations for narrative satisfaction. The universe operates according to physical laws that are indifferent to our desire for climactic resolution. Most astronomical events, even genuinely significant ones, unfold in ways that seem mundane to observers who weren't trained to recognize their subtle but important implications. NASA's follow-up statement, released 12 hours after closest approach, provided technical details that satisfied scientific curiosity while frustrating public expectations for dramatic revelation. Preliminary analysis of Mars orbital data indicates minor variations in ionospheric density consistent with expected interactions between Atlas's ion tail and Mars's magnetosphere. No structural damage to orbital assets detected. Surface operations continuing nominally. The language was precise, professional, and utterly devoid of the cosmic drama that months of speculation had led the public to expect. Where were the stunning images of Atlas blazing past Mars? Where were the electromagnetic light shows that should have been visible from Earth-based telescopes? Where were the obvious signs that something historically significant had occurred? The disappointing reality was that most of the dramatic phenomena people expected would have been largely invisible to casual observation. Ionospheric density variations, while scientifically important, don't produce visual spectacles that translate well to social media. Magnetosphere interactions, however significant for understanding interstellar object behavior, generate data rather than imagery. Professional astronomers understood that the most important consequences of Atlas's Mars encounter might not become apparent for months or even years. The subtle gravitational perturbations, the trace atmospheric chemistry changes, the long-term effects on Mars's electromagnetic environment, all of these required careful analysis of data that would be collected over extended observation periods. But public attention operates according to news cycle dynamics that demand immediate gratification. The story of Atlas, which had sustained media interest for months through mystery and speculation, suddenly lost its narrative momentum when the October 3rd encounter failed to provide obvious drama. The absence of spectacle created an information vacuum that conspiracy theories rushed to fill. If nothing dramatic had occurred, skeptics argued, why had space agencies been so secretive about their observational plans? Why were there so few publicly released images from the encounter? Why did official statements sound like they were hiding something behind technical jargon? Amateur astronomers who had spent weeks preparing for the encounter found themselves in the awkward position of having captured images that showed nothing particularly remarkable. Their telescopes had documented Atlas's passage near Mars, but the visual evidence looked disappointingly similar to computational predictions that had been available for months. The most sophisticated ground-based observatories faced similar challenges in translating their data into public understanding. The spectroscopic measurements that revealed subtle changes in Atlas's emission patterns were scientifically valuable, but visually unimpressive. Radio telescope arrays detected variations in plasma density around Mars, but these discoveries couldn't be easily converted into the kind of dramatic imagery that captures public imagination. Social media algorithms, designed to promote engagement rather than education, began amplifying increasingly elaborate theories about what space agencies weren't telling the public. The mundane reality of a successful scientific observation campaign was reframed as evidence of institutional secrecy. The careful, methodical approach that characterizes professional astronomy was interpreted as deliberate obfuscation. Congressional representatives, many of whom had used Atlas as a platform for discussing space funding and planetary defense, found themselves in the uncomfortable position of having promised their constituents dramatic revelations that failed to materialize. House Science Committee hearings that had been scheduled to address the Atlas crisis were hastily rebranded as routine oversight sessions on NASA's Mars exploration programs. The media coverage reflected this shift from crisis to anticlimax with remarkable speed. Cable news networks that had prepared extensive Atlas encounter programming found themselves with hours of airtime to fill and very little dramatic content to justify the coverage. Expert panels that had been assembled to discuss cosmic catastrophes instead found themselves explaining why the absence of drama was actually the most likely outcome. The scientific community faced its own public relations challenges. Researchers who had spent months preparing for Atlas observations found that their preliminary results, while scientifically interesting, didn't generate the kind of public excitement that translates into continued funding support. The successful prediction of a non-catastrophic encounter was somehow less compelling than unsuccessful predictions of disaster would have been. International cooperation in Atlas observations, which had represented one of the most comprehensive multinational astronomical campaigns in history, received minimal media coverage precisely because it had functioned so smoothly. The coordination between NASA, ESA, JAXA, and other space agencies had prevented the kind of conflicting information releases that might have sustained public interest through controversy. The James Webb Space Telescope's infrared observations of Atlas during the Mars encounter produced some of the highest resolution images of an interstellar comet ever captured, but these scientific triumphs were overshadowed by public disappointment that the images didn't show obvious signs of cosmic catastrophe. The subtle spectral signatures that reveal the exotic chemistry of Atlas's nucleus were far less visually compelling than the dramatic impact scenarios that had dominated pre-encounter speculation. Amateur radio operators who had prepared to monitor Mars communication networks for signs of electromagnetic disruption found themselves documenting routine spacecraft operations instead of cosmic chaos. Their sophisticated monitoring setups, established to capture evidence of historical significance, instead recorded the mundane but reassuring normalcy of continued Mars exploration activities. The October 3rd non-event began to take on symbolic significance that transcended its astronomical importance. Social critics pointed to the Atlas anticlimax as evidence of broader institutional failures in science communication, arguing that researchers and space agencies had failed to properly manage public expectations for what was always most likely to be a scientifically interesting but visually unremarkable event. Educational institutions found themselves grappling with student disappointment that mirrored the broader public reaction. Astronomy classes that had been following Atlas for months as a real-time case study in interstellar object behavior found their students losing interest once the encounter failed to produce obvious drama. Teachers struggled to maintain engagement with the subtle but important scientific discoveries that the encounter had actually generated. The long-term implications for public support of space science became a source of concern within the astronomical community. If the most dramatic interstellar visitor in recorded history could pass through the inner solar system without generating sustained public interest, how would future missions compete for attention and funding against more immediately compelling terrestrial concerns? Yet, perhaps most troubling was the speed with which public attention shifted from Atlas to other topics once the encounter proved less dramatic than expected. The comet, which had dominated astronomical news cycles for months, virtually disappeared from mainstream media coverage within weeks of its Mars encounter. The scientific analysis of the encounter data, which would ultimately prove far more valuable than any dramatic impact scenario, proceeded largely outside public awareness. But this rapid shift in attention may have blinded us to subtle signs that Atlas's influence on our solar system was far from over. What if the quiet passage near Mars was merely the opening movement in a longer, more complex cosmic symphony? What if the real story of Atlas was just beginning, hidden behind layers of institutional secrecy and public indifference? Part 13. Atlas as the Messenger. Throughout human history, comets have served as cosmic punctuation marks in the narrative of civilization, harbingers of change, omens of transformation, messengers from realms beyond terrestrial comprehension. Ancient astronomers interpreted their appearances as communications from divine powers, warnings encoded in celestial fire that demanded careful interpretation by those wise enough to read the language of the heavens. Atlas arrives in our solar system carrying credentials that no previous comet has possessed. This is not a familiar member of our Sun's extended family, following predictable orbits that can be calculated decades in advance. This is a genuine alien, a visitor from stellar distances so vast that it carries within its nucleus the chemical signatures of stellar environments that may no longer exist, stellar systems that died before Earth's continents assumed their current configurations. The message that Atlas carries is written in a language older than terrestrial biology, the language of atomic structure and molecular bonds, of isotopic ratios and crystalline matrices that formed under conditions that never existed anywhere in our solar system. Every spectrographic analysis of Atlas's emissions reveals chemical signatures that tell stories of alien stellar winds, exotic radiation environments, and gravitational conditions that shaped matter according to physical laws operating at extremes our solar system has never experienced. But what if Atlas's message transcends mere chemistry? What if the patterns we've been observing, the erratic brightness variations, the unusual coma geometry, the unexpectedly massive carbon dioxide emissions, represent something more structured than random comet behavior? What if we're witnessing the first attempts at interstellar communication using a medium we never thought to monitor, the controlled sublimation of exotic ices? Consider the possibility that intelligence could manipulate cometary emissions in ways that create detectable patterns across interstellar distances. A civilization that had mastered large-scale engineering might be capable of embedding information in the orbital and emission characteristics of objects launched between stellar systems. The message would unfold over months or years as the object approached our Sun, creating a slow-motion signal that would eventually be detectable by any technological civilization monitoring their solar system. The mathematics of such communication would be elegant in their simplicity. Binary information could be encoded in brightness, variations that follow patterns distinguishable from natural fluctuations. Complex data could be embedded in spectroscopic signatures that reveal themselves only through careful analysis of emission line ratios. Even the object's trajectory could carry information, with subtle course corrections during approach creating geometric patterns that would be unmistakable signatures of artificial control. Atlas's behavior, viewed from this perspective, takes on new significance. The massive carbon dioxide coma that has puzzled astronomers could represent not just unusual sublimation, but controlled gas release designed to maximize the object's visibility and ensure detection by technological civilizations. The erratic brightness patterns that don't match standard comet models could be structured signals waiting for proper mathematical analysis to reveal their embedded message. The timing of Atlas's arrival, during a period when humanity has finally developed the technological sophistication to conduct detailed spectroscopic analysis of interstellar objects, might be more than cosmic coincidence. If the object were launched from its origin star system thousands of years ago, its trajectory would have been calculated to arrive at our solar system during a narrow window when our technological development made us capable of receiving and interpreting sophisticated chemical messages. NASA's James Webb Space Telescope represents humanity's most advanced instrument for analyzing the chemical composition of distant objects. The timing of Atlas's arrival, just as this revolutionary observatory becomes operational, creates conditions where we can extract more information from a single interstellar visitor than would have been possible even a decade earlier. If Atlas carries an embedded message, we may be the first generation of humans capable of decoding it. The European Space Agency's coordinated observation campaigns have generated datasets that contain more information about an individual interstellar object than has ever been collected in human history. Hidden within the terabytes of spectroscopic data, orbital measurements, and emission analysis might be patterns that reveal themselves only through computational analysis techniques that didn't exist when previous interstellar visitors like Oumuamua passed through our solar system. But decoding a potential interstellar message requires abandoning anthropocentric assumptions about communication protocols. The signals might be embedded in mathematical relationships that transcend language barriers, prime number sequences hidden in brightness variations, geometric constants encoded in spectral line ratios, physical constants expressed through isotopic compositions that could only result from artificial manipulation. The challenge lies in distinguishing between natural patterns and artificial signals in phenomena that already stretch the boundaries of our understanding. Interstellar objects inherently exhibit behavior that doesn't match solar system norms, because they formed under different stellar conditions and followed different evolutionary paths. Separating genuine anomalies from exotic but natural processes requires analytical techniques that are still being developed. Amateur astronomers and citizen science groups have been contributing observational data that professional observatories might miss due to scheduling constraints and limited telescope time. If ATLAS carries embedded signals, they might be most apparent in long-term monitoring data collected by dedicated amateur observers who can track the object continuously rather than during brief professional observation windows. The SETI Institute has quietly begun applying signal analysis techniques developed for radio astronomy to the ATLAS datasets, searching for patterns that might indicate artificial manipulation of the object's behavior. While no results have been publicly announced, the mere fact that such analysis is being conducted suggests that the possibility of ATLAS serving as an interstellar communications platform is being taken seriously by researchers experienced in searching for extraterrestrial intelligence. The message, if it exists, might not be intended for immediate comprehension. Interstellar communication across thousands of years would necessarily involve concepts and information that might require generations of human technological development to fully understand. ATLAS might be delivering a message that will only become comprehensible when our mathematical and scientific knowledge advances to levels that match the civilization that sent it. The psychological implications of such a discovery would transform human civilization in ways that dwarf any physical effects ATLAS might have on Mars or other planets. Confirmation that we are not alone in the universe, delivered through the patient arrival of an interstellar message, would force humanity to reconceptualize our place in the cosmic community and our responsibilities as members of a galaxy-spanning network of intelligent civilizations. But the absence of an obvious message shouldn't be interpreted as evidence that no message exists. The most sophisticated communication might be embedded in aspects of ATLAS's behavior that will only become apparent through analysis techniques that haven't been invented yet. Future generations might look back at our current ATLAS observations and marvel at how much information we failed to extract from the richest interstellar dataset in human history. International cooperation in ATLAS research has created unprecedented opportunities for global collaboration in potential message decoding efforts. If the object carries information intended for all of humanity rather than any single nation, the distributed nature of current observation campaigns ensures that no single government or institution could suppress or monopolize access to interstellar intelligence. The ATLAS encounter might be serving as an inadvertent test of our civilization's capacity for rational analysis under conditions of uncertainty and speculation. Our response to this interstellar visitor, the theories we've generated, the fears we've expressed, the institutions we've trusted or suspected, might reveal fundamental weaknesses in our collective decision-making processes that could prove catastrophic when genuine cosmic threats eventually emerge. The speed with which ATLAS became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence suggests that we've developed information processing systems that are more vulnerable to manipulation than we realized. Social media algorithms that amplify dramatic content over accurate content have created conditions where speculation can overwhelm evidence faster than scientific analysis can counter misinformation. The October 3rd encounter represents more than just an astronomical event. It's become a mirror that reflects our civilization's relationship with the unknown, our trust in expertise, and our ability to distinguish between genuine mysteries and manufactured crises. The lessons we draw from ATLAS's passage through our solar system might prove more significant than any physical effects the object has on Mars or other planets. Perhaps the most profound realization emerging from the ATLAS encounter is temporal, that our solar system exists within galactic neighborhoods, where interstellar visitors are routine rather than extraordinary events. The rarity of such objects in human historical records reflects not their actual scarcity, but the brief duration of our technological civilization relative to astronomical timescales. If ATLAS represents the first of many interstellar visitors that our expanding detection capabilities will identify in coming decades, then our current speculation and institutional responses might be establishing precedents for how humanity will address an entire class of cosmic encounters. The frameworks we develop for analyzing ATLAS, both scientific and social, will shape our responses to future interstellar visitors for generations to come. The datasets generated by ATLAS observations will continue providing research opportunities long after the object itself has departed our solar system. The spectroscopic measurements, orbital calculations, and emission analyses represent the most comprehensive study of an interstellar object ever conducted by human civilization. Hidden within these data might be insights that will only become apparent when future technological developments provide new analytical capabilities. Graduate students and researchers decades from now might discover patterns in the ATLAS data that reveal information we currently lack the mathematical or theoretical frameworks to recognize. The most significant discoveries from ATLAS's visit to our solar system might not emerge until the 2040s or beyond, when scientific advances allow us to extract information from observations we're conducting today without fully understanding their ultimate implications. The international cooperation that ATLAS has inspired among space agencies, research institutions, and amateur astronomy communities represents an unprecedented experiment in global coordination around cosmic phenomena. The protocols developed for sharing ATLAS data and coordinating observation campaigns might serve as templates for managing future encounters with interstellar visitors or other cosmic events that transcend national boundaries. But cooperation also creates vulnerabilities. If our current ATLAS research is missing crucial information or misinterpreting significant patterns, the coordinated nature of current efforts might amplify these errors across multiple institutions and nations. The same coordination that makes comprehensive analysis possible could also make systematic mistakes more difficult to recognize and correct. The amateur astronomy contributions to ATLAS research have demonstrated the continuing importance of distributed observation networks that can monitor objects continuously rather than during brief professional telescope windows. Future interstellar visitors might be best studied through coordinated campaigns that combine professional capabilities with amateur dedication and geographic distribution. Educational institutions that have used ATLAS as a real-time case study in interstellar object behavior have created pedagogical resources that will influence how future generations of scientists approach cosmic mysteries. The teaching materials, observation protocols, and analytical techniques developed during ATLAS research will shape scientific education for decades to come. The psychological and cultural impacts of ATLAS might prove as enduring as its scientific contributions. This interstellar visitor has forced humanity to confront our cosmic isolation in ways that purely theoretical discussions never could. The simple existence of an object from another stellar system has made interstellar space seem less empty and alien civilizations seem more possible. Public opinion polls conducted during ATLAS's approach have documented shifting attitudes towards space exploration, funding, planetary defense programs, and international cooperation in scientific research. These attitudinal changes, triggered by a single cosmic event, might influence policy decisions and resource allocation for decades to come. The ATLAS encounter has also revealed the extent to which modern technological civilization depends on predictable cosmic conditions. Our spacecraft, communication systems, and even terrestrial infrastructure were designed under the assumption that space remains essentially static between major solar storms and asteroid impacts. Interstellar visitors introduce additional variables that our engineering and risk assessment systems weren't designed to accommodate. Future space missions will need to account for the possibility of encountering debris fields, electromagnetic anomalies, or chemical contamination left behind by interstellar visitors. Mission planning protocols that worked adequately for solar system exploration might prove insufficient for operating in a cosmic environment that includes regular interstellar traffic. The legal and ethical frameworks that govern space exploration were crafted under the assumption that cosmic encounters would involve objects and phenomena that originated within our solar system. ATLAS has introduced questions about sovereignty, environmental protection, and scientific responsibility that existing space law doesn't adequately address. If future interstellar visitors carry embedded messages, technological artifacts, or biological materials, humanity will need new international agreements that balance scientific investigation with planetary protection, national security concerns with information sharing, and immediate research opportunities with long-term consequences for human civilization. The Atlas encounter represents humanity's graduation from a solar system-scale civilization to participants in galactic-scale phenomena. Whether we've passed or failed this cosmic examination might not become apparent for decades, but our response to this first major test will establish patterns that influence our species' development for generations to come. As Atlas continues its journey toward the outer solar system, and eventually back to interstellar space, it carries with it not just the chemical signatures of an alien stellar environment, but also the reflected light and radio emissions from a young technological civilization taking its first tentative steps toward cosmic maturity. Future interstellar visitors might detect these signatures and draw their own conclusions about humanity's readiness for membership in whatever cosmic community exists among the stars. October 3rd, 2025, might be remembered not as the day Mars was threatened by an interstellar visitor, but as the day humanity began to understand that we are not alone in a universe full of wandering messengers carrying news from distant worlds. The real question isn't what Atlas might do to Mars, but what it has already done to us, and whether we're prepared for the next cosmic visitor that follows in its ancient, starlit wake. The worst-case scenario for Atlas might not be planetary catastrophe or electromagnetic chaos. It might be that we've learned nothing from this encounter about our cosmic vulnerability, our institutional limitations, and our desperate need to develop better frameworks for understanding our place in a universe that is far stranger, far more active, and far more dangerous than our brief technological civilization has yet realized. Part 14. Closing speculation. What if we're missing the real story? October 3rd has passed. Mars continues its ancient orbit. The spacecraft that monitor the red planet continue transmitting their routine observations back to Earth. Atlas proceeds on its calculated trajectory toward the outer solar system, its moment of closest approach to our neighbouring planet, now a matter of historical record rather than future speculation. And yet, in the quiet aftermath of an encounter that failed to deliver the cosmic drama that months of speculation had promised, a more unsettling possibility begins to emerge. What if our entire framework for understanding Atlas, our focus on impact scenarios, atmospheric disruptions, and potential contamination, represents a fundamental misunderstanding of what we're actually witnessing? What if the real story of Atlas isn't about what might happen to Mars, but about what has already happened to our information systems, our decision-making processes, and our collective ability to distinguish between genuine cosmic threats and manufactured crises? The evidence for this alternative interpretation lies not in telescopic data or spacecraft telemetry, but in the patterns of institutional behavior that have surrounded Atlas since its discovery. Consider the careful timing of information releases, the coordination between international space agencies that normally compete for resources and recognition, the unusual level of congressional interest in what should have been a routine astronomical observation campaign. Space agencies that typically rush to publicize their most dramatic discoveries have been conspicuously measured in their Atlas communications. The James Webb Space Telescope's observations of the object, conducted in August, remain under analysis months later, despite the revolutionary capabilities of the instrument and the presumed significance of studying humanity's first well-documented interstellar visitor with such sophisticated equipment. NASA's Science Mission Directorate, normally eager to share spectacular images and breakthrough discoveries with tax-paying publics, has provided primarily technical briefings and trajectory updates rather than the kind of inspirational content that typically accompanies major astronomical events. The European Space Agency, with its different political constraints and communication traditions, has followed remarkably similar protocols, suggesting coordination that transcends normal institutional boundaries. The absence of spectacular imagery from the October 3rd encounter might not represent a failure of observation campaigns, but the success of information management strategies that we're not meant to recognize. If the most significant aspects of Atlas's passage near Mars occurred in spectral bands or at temporal resolutions that don't translate into publicly compelling content, the lack of dramatic footage could be entirely intentional. Professional astronomers, who normally compete vigorously for publication priority and media attention when dealing with significant discoveries, have maintained an unusual level of collective discretion regarding ATLAS research. Preliminary findings that would typically be announced at press conferences and published in rapid-release journals have instead followed more deliberate review processes that prioritize institutional coordination over individual recognition. The amateur astronomy community, typically eager to share observations that might challenge or complement professional research, has produced surprisingly little independent analysis of ATLAS, despite the object's accessibility to sophisticated backyard equipment. This silence might reflect not lack of interest, but pressure from professional networks to coordinate observations rather than compete for attention. Congressional oversight of space agencies, while publicly focused on routine budgetary and policy questions, may be addressing classified aspects of ATLAS research that never appear in public hearing transcripts. The space science committees that normally micromanage NASA's most expensive missions have shown unusual deference to agency expertise regarding ATLAS observation strategies and data release schedules. International space law provides frameworks for managing information about potentially hazardous objects, but these protocols were developed with conventional near-Earth asteroids in mind, not interstellar visitors whose origins and compositions might reveal information that transcends normal astronomical significance. If ATLAS carries implications for national security or international relations, existing treaties might not provide adequate guidance for information management. The possibility that we're witnessing the first coordinated global response to an interstellar visitor carrying information too sensitive for routine public disclosure would explain many of the anomalies in official ATLAS coverage. Space agencies, intelligence services, and political institutions might be navigating unprecedented challenges that have no historical precedents and no established protocols. But information control, if it exists, might serve purposes beyond simple secrecy. If ATLAS carries embedded messages or technological information that humanity is not yet prepared to understand or utilize safely, the managed disclosure might represent responsible stewardship rather than institutional deception. The gradual release of increasingly complex information might be designed to prepare global civilization for revelations that could be destabilizing if delivered without proper preparation. The timeline for such managed disclosure could span decades, with each phase of revelation calibrated to match humanity's technological and social development. The current focus on ATLAS as an interesting but ultimately routine astronomical phenomenon might represent the opening phase of a much longer educational process designed to prepare us for eventual recognition of the object's true significance. Educational institutions and scientific organizations might be quietly preparing curricular and research programs that will eventually address the implications of interstellar communication and cosmic citizenship, but only after political and social institutions develop frameworks for managing such profound expansions of human knowledge. The apparent normalcy of current ATLAS research might conceal preparation for extraordinary future revelations. Yet even managed disclosure assumes that ATLAS carries information or implications significant enough to justify such elaborate coordination. What if the most disturbing possibility is simpler, that ATLAS represents exactly what conventional astronomy suggests, a routine interstellar object following predictable physical laws, and our tendency to seek hidden significance reveals dangerous vulnerabilities in our information processing systems. The readiness with which conspiracy theories and alternative narratives have attached themselves to ATLAS might indicate that our technological civilization has become dangerously susceptible to disinformation campaigns that exploit our psychological need for cosmic significance. If a genuinely routine astronomical event can generate such elaborate speculation, how would we respond to actual cosmic threats or legitimate interstellar messages? The ATLAS encounter might be serving as an inadvertent test of our civilization's capacity for rational analysis under conditions of uncertainty and speculation. Our response to this interstellar visitor, the theories we've generated, the fears we've expressed, the institutions we've trusted or suspected, might reveal fundamental weaknesses in our collective decision-making processes that could prove catastrophic when genuine cosmic threats eventually emerge. The speed with which ATLAS became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence suggests that we've developed information processing systems that are more vulnerable to manipulation than we realized. Social media algorithms that amplify dramatic content over accurate content have created conditions where speculation can overwhelm evidence faster than scientific analysis can counter misinformation. The October 3rd encounter represents more than just an astronomical event. It's become a mirror that reflects our civilization's relationship with the unknown, our trust in expertise, and our ability to distinguish between genuine mysteries and manufactured crises. The lessons we draw from Atlas's passage through our solar system might prove more significant than any physical effects the object has on Mars or other planets. Perhaps the most profound realization emerging from the Atlas encounter is temporal, that our solar system exists within galactic neighborhoods where interstellar visitors are routine rather than extraordinary events. The rarity of such objects in human historical records reflects not their actual scarcity, but the brief duration of our technological civilization relative to astronomical timescales. If Atlas represents the first of many interstellar visitors that our expanding detection capabilities will identify in coming decades, then our current speculation and institutional responses might be establishing precedents for how humanity will address an entire class of cosmic encounters. The frameworks we develop for analyzing Atlas, both scientific and social, will shape our responses to future interstellar visitors for generations to come. The data sets generated by Atlas observations will continue providing research opportunities long after the object itself has departed our solar system. The spectroscopic measurements, orbital calculations, and emission analyses represent the most comprehensive study of an interstellar object ever conducted by human civilization. Hidden within these data might be insights that will only become apparent when future technological developments provide new analytical capabilities. Graduate students and researchers decades from now might discover patterns in the Atlas data that reveal information we currently lack the mathematical or theoretical frameworks to recognize. The most significant discoveries from Atlas's visit to our solar system might not emerge until the 2040s or beyond, when scientific advances allow us to extract information from observations we're conducting today without fully understanding their ultimate implications. The international cooperation that Atlas has inspired among space agencies, research institutions, and amateur astronomy communities represents an unprecedented experiment in global coordination around cosmic phenomena. The protocols developed for sharing Atlas data and coordinating observation campaigns might serve as templates for managing future encounters with interstellar visitors or other cosmic events that transcend national boundaries. But cooperation also creates vulnerabilities. If our current Atlas research is missing crucial information or misinterpreting significant patterns, the coordinated nature of current efforts might amplify these errors across multiple institutions and nations. The same coordination that makes comprehensive analysis possible could also make systematic mistakes more difficult to recognize and correct. The amateur astronomy contributions to Atlas research have demonstrated the continuing importance of distributed observation networks that can monitor objects continuously rather than during brief professional telescope windows. Future interstellar visitors might be best studied through coordinated campaigns that combine professional capabilities with amateur dedication and geographic distribution. Educational institutions that have used Atlas as a real-time case study in interstellar object behavior have created pedagogical resources that will influence how future generations of scientists approach cosmic mysteries. The teaching materials, observation protocols, and analytical techniques developed during Atlas research will shape scientific education for decades to come. The psychological and cultural impacts of Atlas might prove as enduring as its scientific contributions. This interstellar visitor has forced humanity to confront our cosmic isolation in ways that purely theoretical discussions never could. The simple existence of an object from another stellar system has made interstellar space seem less empty and alien civilizations seem more possible. Public opinion polls conducted during Atlas's approach have documented shifting attitudes towards space exploration funding, planetary defense programs, and international cooperation in scientific research. These attitudinal changes, triggered by a single cosmic event, might influence policy decisions and resource allocation for decades to come. The Atlas encounter has also revealed the extent to which modern technological civilization depends on predictable cosmic conditions. Our spacecraft, communication systems, and even terrestrial infrastructure were designed under the assumption that space remains essentially static between major solar storms and asteroid impacts. Interstellar visitors introduce additional variables that our engineering and risk assessment systems weren't designed to accommodate. Future space missions will need to account for the possibility of encountering debris fields, electromagnetic anomalies, or chemical contamination left behind by interstellar visitors. Mission planning protocols that worked adequately for solar system exploration might prove insufficient for operating in a cosmic environment that includes regular interstellar traffic. The legal and ethical frameworks that govern space exploration were crafted under the assumption that cosmic encounters would involve objects and phenomena that originated within our solar system. ATLAS has introduced questions about sovereignty, environmental protection, and scientific responsibility that existing space law doesn't adequately address. If future interstellar visitors carry embedded messages, technological artifacts, or biological materials, humanity will need new international agreements that balance scientific investigation with planetary protection, national security concerns with information sharing, and immediate research opportunities with long-term consequences for human civilization. The Atlas encounter represents humanity's graduation from a solar system-scale civilization to participants in galactic-scale phenomena. Whether we've passed or failed this cosmic examination might not become apparent for decades, but our response to this first major test will establish patterns that influence our species' development for generations to come. As Atlas continues its journey toward the outer solar system and eventually back to interstellar space, it carries with it not just the chemical signatures of an alien stellar environment, but also the reflected light and radio emissions from a young technological civilization taking its first tentative steps toward cosmic maturity. Future interstellar visitors might detect these signatures and draw their own conclusions about humanity's readiness for membership in whatever cosmic community exists among the stars. October 3rd, 2025, might be remembered not as the day Mars was threatened by an interstellar visitor, but as the day humanity began to understand that we are not alone in a universe full of wandering messengers carrying news from distant worlds. The real question isn't what Atlas might do to Mars, but what it has already done to us, and whether we're prepared for the next cosmic visitor that follows in its ancient starlit wake. The worst-case scenario for Atlas might not be planetary catastrophe or electromagnetic chaos. It might be that we've learned nothing from this encounter about our cosmic vulnerability, our institutional limitations, and our desperate need to develop better frameworks for understanding our place in a universe that is far stranger, far more active, and far more dangerous than our brief technological civilization has yet realized. The silence that follows October 3rd might be the most ominous sound in human history, not the silence of space, which we've always known was there, but the silence of missed opportunities, ignored warnings, and questions we were too afraid to ask. In that silence, Atlas continues its journey back to the stars, carrying with it the fading radio signatures of a young civilization that had its first chance to prove it was ready for cosmic citizenship. Whether we passed that test remains to be seen. The universe, patient and indifferent, will undoubtedly provide more opportunities. The question is whether we'll recognize them when they arrive, or whether we'll continue to mistake the most important messages for background noise in the cosmic symphony that plays eternally around us. Sometimes the most profound revelations come not in the form of dramatic catastrophes, but in the quiet realization that we've been looking in all the wrong places for all the wrong things. Atlas may have given us exactly what we needed to survive as a spacefaring species. We just haven't figured out what that gift was yet. The worst-case scenario isn't that Atlas destroys Mars. It's that Atlas saves humanity, and we never even notice.